Sorry, there is a bit of.
Let me see. You're a co-host. Yeah, you must be able to share.
Yeah, no, I think it is my thing. Okay, let me do this. It's a new laptop. Sorry, and apparently, since I haven't shared screen, okay, sorry about that. I'll have to quit Zoom and reopen it.
Okay, yeah, it asks for permissions. Yes, it happens. Meanwhile, people are gathering, so I think it's fine to be a couple of minutes late.
So we are already cutting to the time right now. Okay, very good.
But I think we can be rather relaxed in a sense that.
Sure, I understand.
I mean, if you lose 5 minutes per talk, then there's not much coffee break left in the end. So.
We will.
So, Andrei, can you also record? Just
no, because I'm not a host, not even co-host.
Oh, okay.
That can be changed.
This can be this can be fixed.
Okay. Could you make me co-host again?
Yes,
please?
yes. So yeah, okay.
Now I think good.
Working now?
Yes. Yes.
Okay, good. Sorry about this thing. It's just a new laptop, and I thought that something would go wrong, but okay. Now it's working. But okay, so yeah, I'm Viktor Gorbenko from EPFL. I'm going to talk about infrared effects in de Sitter and in inflation. Let me go straight to the outline. I will start with reviewing the problem of infrared divergences in de Sitter space and in inflation, and what the status is. And then we will develop a new systematic formalism for quantum field theories in de Sitter-like spacetimes, which resolves this problem. And then, okay, we will focus actually on a particular theory in rigid of a light scalar field and rigid de Sitter space, but then the claim is that the approach works more generally in gravity, at least in perturbative regime, and in inflation, in regime when it's not eternal. If I have time, I'll try to talk about it. Okay, given the number of slides that I have, probably I will not have time. Yeah, don't be surprised if I start skipping slides. Towards the end, it's kind of planned like this. I put a bit more stuff in case there are questions, or in case, you know, people see slides, maybe later on the web page, there's a bit more information they'll be able to communicate. And yeah, this is work in my paper with Leonardo Senatore, and I'll see if I have time, I'll mention some work in progress. Good. So exponentially expanding spacetimes that are close to de Sitter are relevant for the early universe, as well as for the present day expansion. And I think there is no need to review it for this conference. However, when it comes to stability of the de Sitter space, the community appears to be very polarized. And many people would agree that on some, you know, non-perturbative quantum gravity level, de Sitter space eventually decays. But the discussion is not at this level yet. The much more basic level of just quantum field theory, perturbative quantum field theory in a rigid de Sitter space, or if we do inflation or gravity perturbatively in H over M Planck. Okay, so I'm not talking about some extreme complicated situation. Still, many people disagree on the point whether this setup is under control. So if you ask somebody, you know, I just weakly coupled quantum field theories on de Sitter space are stable, there are many people who will tell you like, yes, obviously yes, and there are people who will tell you obviously no, and somehow very few people who think about it at all are neutral on this point. You know, I'm not going to do any complete review, but say in the recent paper of Polakov and Popov, it just came out a couple days ago, they after some calculation, they arrived at this conclusion that I quoted from this paper, that like quantum field theory, or odd dimensional de Sitter space, does not make any sense. Okay, and my point of view is that we as a community, we should settle on this, let's say, relatively simple questions, okay, just about quantum field theory and perturbative gravity on the Sitter space. It sounds like something we can agree on, something that shouldn't be controversial, before we can attack maybe some deeper non-perturbative quantum gravity questions that eventually we also want to understand. So this is the goal of today's talk, okay? Not the non-perturbative quantum gravity questions, but these more basic things. So many concerns, I think, they originate from the following technical issue, that if you do a perturbative, just Feynman diagram calculation, and the theories of light, massless scalars, of gravitons, or inflation, you always get some sort of logs in perturbation theory. These logs, they grow with time and also with your, say, momentum, when spatial momentum goes to zero. And this sometimes leads to breakdown of perturbation. Okay? So I think this is the technical issue that somehow triggers concerns. But of course, breakdown of perturbation theory and so on does not mean that there is a physical problem. Okay, it means that the method of computation is bad. And I think that it's best to really understand the problem and its resolution. One concrete case first. And then I argue it works the same way in these other questions, that in other cases that say we listed here and that are of interest for us. So we're going to consider a light scalar field on rigid de Sitter space. Okay, no gravity, and Planck is taken to infinity. Hubble is constant. Let's take, say, for W slicing, put this scalar field with some potential, and really in this talk I will focus on m squared phi squared plus lambda phi the potential, and we will go in this regime where mass is much smaller than Hubble, and also coupling constant is small. Okay, so we have at least naively or in flat space this theory, we would have a full perturbative control, right? We wouldn't have any questions if lambda is positive that this theory is well defined. And our goal here in the Sitter is to compute correlation functions of this field phi at long distances, so that the physical distance is taken to infinity. Okay, or you can think of it as late time correlators, similar to what we measure in inflation. And first, we focus on equal time. Okay, we can do non-equal time, but we focus on equal just to get started. First, okay, we have a small coupling, right? So let's do the calculation perturbative as we would do in class. And there are very similar diagrammatic techniques called Schwingel-Kelder, showing informalism. That some rules how to generate Feynman diagrams, and okay, I draw here a few Feynman diagrams, say for 2-point functions. So time goes upwards, natural inflation. Then this red line is, think of it as some reheating surface, a future boundary of this region, the Sitter space, on which I insert my correlators at spatial coordinates x and y. And I do perturbation theory. So say if the free field contribution, say we scale this as 1, then say we do this one loop. And when we have this loop, we have the propagator. For example, here we can keep time as a time variable and spatial coordinates x, we can Fourier transform the 3-dimensional momenta k. And this was a question. We need to take time integrals and k integrals, and both of this k integral and time integral. So that's the behavior of a propagator at small k. Okay, they at small k and at late times, both of these integrals they lead to 1 over m squared divergences. Well, not divergence, but 1 over m squared factors. Okay, they're finite here. They would have been logs if I took exactly massless field, but it's a bit, I think, easier conceptually for now to take a small mass. And we get 1 over m squared contributions, and then we pay price of a coupling constant, we get lambda over m to the 4. And then we go to higher loops, we get like lambda squared over m to the 8, etc., etc. And if mass is small enough, then perturbation theory is divergent. Okay. So that is the problem, and we need alternative formulas. That's what we developed with Leonard in this paper, inspired a lot by older work of Alexei Starobinsky. Good. So the contraction is a little bit complicated. So I think the convener of our session announced that the talks will be very technical. Okay, and I'll try to make it comprehensible, but it's true that the construction is a bit complicated. The, on the upside is that it's quite rigorous on the physical scale. But let me guide you through the steps. So the calculation consists of 4 steps. First, we calculate the wave function. And at this point, we will fix some state. Then we'll separate modes into long and short. Then we derive certain equations, partial differential equations for probability distributions. I will introduce what they are. And then solutions of these equations, they lead us to correlation functions. Okay, so 4 steps. Let me go through these 4 steps, okay, in some level of details. Of course, I'll drop most of the details, but I hope I'll give you some taste of how it works, okay? So really quickly, basic facts about the Sitter space. It's expanding part. We keep this metric. We can use FRW time or conformal time. I will be switching between the two. I hope everyone is familiar with this transformation. So if we look at now at the Penrose diagram, it's a square. Sure, it appeared in this conference before. There is a cosmological horizon, and okay, so this red line is an equal time slice, and we're interested in correlators that are very far away from the horizon, right? So the Penrose diagram looks fine at the Sitter space. In fact, of course, this slice becomes arbitrarily large. Okay, and again, for most people in this audience, I think, are familiar, but we can also draw some cartoon of the Sitter space, how the physical distance changes with the scale factor or with time, right? And the modes that start. So here, on this diagram, horizon scale keeps constant, but every mode of a given fixed wavelengths, fixed k in our Fourier transform, its physical size evolves, right? It comes out of horizon, and then eventually, when we measure it, it is very far outside of the horizon. Okay? And the definition of long modes is when A delta x much bigger than Hubble to -1, or k much smaller than A Hubble, right? Okay, and then I promise that we will fix the state, and the state for now, for this part of the calculation, will be fixed so that it looks like Minkowski space vacuum at very short distances. Okay, so that's some analog of Bunch-Davies vacuum interaction theory. Then we're going to argue after our calculation that small perturbation of the state, they do not change the picture dramatically, right? But first we do calculation of fixed state. So moreover, first we start with just calculating the wave function of that state. Okay, and the first important technical point is the calculation of the wave function itself, that I call psi Bunch-Davies here, does not suffer from infrared divergence. Okay, so the calculation of wave function, there is also wave function depends on time and on source fields, these 3-dimensional fields, and we can insert them in some surface of given time. It is now in-out perturbation theory. It's a wave function, it's a real-time evolution. There is no in-in, it's an in-out perturbation theory, similar to what we do for an S matrix in flat space. And here the propagator is different because we have different boundary conditions for our Green's function. So propagator is different. It so happens that at small k it goes to a constant as opposed to going to this 1/k to 3 minus m squared. So there are no infrared divergences. And similar, there are also no infrared divergence when we take integrals over time. So it can be seen in a direct de Sitter calculation, okay, I'm not going to it in the paper. We prove it carefully, but for just a little shortcut for people familiar with maybe with ADS CFT or with ADS physics, this relation that the Bunch-Davies wave function is actually related by analytic continuation. Specified here to a partition function of corresponding theory on Euclidean non-de Sitter space. And then, okay, non-de Sitter space, you do calculation Andrei Linde IR divergences. Okay, that's a known technical statement for light scalar fields. Good. So we can calculate the wave function. There are no IR divergences hit us in the face. Now, in which sense the wave function is perturbed? Okay, so here let's write the schematically expression for the logarithm of the wave function when time becomes late, right? That's conformal time goes to 0, becomes late. So there will be some term, leading terms that go like 1 over eta cube. They purely imaginary. They consider the potential and some purely local terms in fields. Then there will be some the terms the 2 powers of eta small, and then they have gradient corrections, and then there will be something that looks like a partition function of some CFT, and then further suppressed terms. So that's the structure. Again, for people familiar with the idea of CFT, this is very analogous. For people not familiar, this is just the result of calculation. Really, these terms and these terms, that's something that's going to play a role in our calculation, right? Never mind this kind of more complicated objects appearing here. Now, when I say that there is that this thing is because you see this thing has different powers of fields, for example, in which sense it is a perturbative expansion in a coupling constant lambda. Well, it is a perturbative expansion. You analyze how these terms look like, as long as the value of fields. We calculate the wave function. So in principle, it should be defined for all possible field configurations, right? But for field configurations such that the value of the field is smaller than this thing here, lambda to minus 1/2. Remember, lambda is a quartic coupling constant, so it's small. So this is a thing that is large, much larger than Hubble. So as long as the field is smaller than this expression, expansion of this in powers of fields is meaningful. And we will see that actually for what we care about, field is going to go like this, lambda minus 1/4. So we satisfy this relation. Good, but it's in this regime where we can use the wave function. And initial condition, they are fixed, as I already said, by demanding that, say, momentum space for given modes of given k, when time goes to minus infinity, that's infinite path, we go to just a Minkowski wave function. That is a uniquely Minkowski vacuum wave function, which is uniquely defined. Good. And then, of course, we got the wave function. If we were in quantum mechanics, we have the wave function in all correlation functions. You just compute them. Here we cannot just get them because getting correlation functions out of the wave function is another path integral, and this path integral is still the divergence. So far, we didn't achieve anything. We want to get correlation functions, we still have error. However, we go to the second step, and that was really the insight of Starobinsky, that we're going to split our field in 2 components, into long and short. So long component is, roughly speaking, it's all the momenta up to some cutoff lambda of t that changes with time. Okay, so more and more modes become long as time goes on. So this epsilon is some small number. It cannot be taken arbitrarily small, and we will see what it is, but it is much smaller than 1. Okay, good. And well, in fact, in details, procedure is a bit more complicated. You shouldn't do the sharp momentum cutoff. You should do something a little bit more similar to what Polchinski does in his famous RG paper. You need to smear a little bit the cutoff to make it analytic. But anyway, the technical details mentioned in the paper, I'm not going to mention them. There is a lot of similarity, at least conceptually, between epsilon and the RG scales. In particular, it will cancel out of all the physical observations. All right, so it's and we will choose epsilon small. In particular, we're going to choose epsilon in this range. So it's small and square root of the coupling constant, but it's not non-perturbatively small. Well, can be non-perturbatively small, but bigger than this non-perturbative number. And then we will do expansion in lambda and in this epsilon. Okay, good. Step 3. Is we define the endpoint distributions for long modes. What is this object? So here I have this Pn that depends on values of n long fields at some fixed coordinate position and at some given time. Okay, and that is done by taking a path integral over the probability density psi star with inserting a bunch of delta functions that fix these values of long modes at a finitely many spatial points. Okay, good. Again, this path integral we cannot take. It is IR divergent, but as a formal object we can define. Now, if we know PNs, then correlation functions of long modes can be computed by regular integrals. Okay, so there is, if we get these PNs, we get the correlation function. At least numerically, there is no more conceptual problem. Okay, it's no longer path integral we need to take. We need to only take a regular integral. So if it's convergent, it can only be taken, right? As I said, we cannot compute them directly, but we can derive an equation which guides their time evolution. Good. So time evolution, we take time derivative. There are two terms that are called traditionally drift and diffusion. Let me focus on the drift term for one-point distribution, some details. Okay, there is some derivation of diffusion term is a bit more common. Diffusion term comes from the action of time derivative on the definition of the long mode. Okay, that kind of propagates all these formulas and sits inside this delta function, defines the speed. But we focus on drift term. For drift term, time derivative acts on the product of the wave functions. Okay, and then here we use Schrödinger equation. We use functional Schrödinger equation. The potential term cancels. We get this expression that's called continuity equation, I guess, in quantum mechanics. And now, because this time derivative is then integrated in the path integral, it's only the long derivative with respect to the long mode survives. Okay, this is clear from here, right? Because it's integrated. When we define this P, we integrate all short modes. So if there is a derivative, short derivative, we can integrate by parts, it dies. Okay, now, when the long derivatives act on the wave function, we know what it is because we know the wave function. This is where we use the knowledge of the wave function. So we call this just a definition. The capital P long is the result of the action of the derivative, functional derivative on the wave function. Then we look at our expression for the wave function. Okay, copy it a little bit here, and we see that the leading term is just the potential term. Okay, sorry, the leading term, the wave function, potential term, then derivatives gives V prime. Okay, and then there's some subleading terms. So we plug in this P, we integrate by parts. Okay, and then the derivative acts on delta function, and then we transform it with derivative phi1. So that's now a regular derivative. Okay. And what we get here, this object is expectation value of this momentum thing that is now just some functional fields, okay? Given, so this bracket with phi1, given the sort of like in a background field method, that the long modes are fixed at finitely many special positions. Here it's one special position. Good. So now we open up a little bit this bracket. We substitute what this P long is. There is a lambda phi cubed, lambda square phi to the 5, and all these terms and some subleading terms. Then we do counting in lambda. This leading term again. Okay, should be careful. I assume for this calculation that phi goes as lambda to the -1/4, as I announced, and then we're going to check that this is indeed the correct regime. But we're now going to do some power counting, assuming that this phi, did I write it here? Sorry, I forgot to write it. That phi goes like Hubble times lambda to -1/4. Good, so this allows us to do some counting of these terms. As you see, they're suppressed as long as this condition on epsilon is satisfied. This thing is smaller than this thing. If epsilon I took too small, that wouldn't work. My expansion would break down, right? But I don't. Remember, I keep this. Very good. Now there are some subtle terms here. For example, 3 long fields can make a short one. Okay, so we need to project. We need to keep this pi long. It only depends on long momentum below the cutoff. But then this phi cube term, this phi long cube term, it has some short momentum. So we need to project, Fourier transform. And the point is that, okay, it's a little bit impressionistic, but the point I want to get you, impressionistic in the sense here I'm showing it can be done precisely, but I'm showing you that to compute this term, we need to know the 2-point distribution, because if we know the 2-point distribution of fields at 2 points, then we can do this convolution with a kernel that projects on momenta smaller than the cutoff, and then hence project our momentum on the long modes. But the crucial point here is when the magic happens. We never need to take non-trivial path integrals of long modes. Every time, basically, the Feynman diagram calculation, the analogous step would have done a path integral, basically, or some correlation of long modes. We just insert a higher point probability distribution and leave it, for better days. This integral, leave it for later. Okay, but for now, we just, every time we need a new long mode, we just insert the higher point probability distribution. So to summarize, we get something like this. Time derivative of this P1, it is some stuff that depends on P1 plus some stuff that depends on P2 plus corrections that come a higher order in lambda and epsilon. Okay, and then there is a diffusion term analogously, a bit more complicated calculation, don't have time to do now. And analogous steps give us a calculation for all PNs. So instead of going to further details, let me get to the final answer, okay? So crucial building blocks are these 1 and 2 field differential operators called gamma I and gamma ij. So gamma I is a differential operator with respect to a long field at a single location. Okay, it's this leading or a second order differential operator. And then gamma ij depends on fields on the 2 locations, I and j. And okay, there is some position dependence. Remember this P, say P2 depends on values of the field at 2 locations and the distance. And then this operator also depends on the distance. And then there is a hierarchy of differential equations. There is an equation for P1 that to leading order. So the red is leading order terms. Leading order in lambda and in epsilon. It only depends on P1. Okay, in P2, leading term all depends on P2, but then as sub-leading terms, there are mixings. Okay, between to keep track of these gradient corrections, for example. But that is okay because we can solve this hierarchy. We solve for P1, then we solve for P2, then we can substitute back here P2 and find correction for P1. Okay. And this can be, can in principle be done to any order in our parameters lambda and epsilon. We also need initial conditions. And initial conditions, okay, they have this form that when time goes to minus infinity, all the P2, for example, becomes P1 times the delta function. That makes sense because at time goes to minus infinity, points collide. Okay, that I was saying here, when we need finitely many terms to solve our PDEs to a given order in the coupling constant, and okay, we can stare a little bit on how the leading order equations is solved. It's a diffusion equation to solve a diffusion equation, or some sort of maybe a better way to phrase it is like a Euclidean version of Schrödinger equation. So we find eigenvalues and eigenfunctions. For all reasonable potentials, the spectrum is bounded from below. So it's a well-defined problem. Okay, how much time do I have? I have like 3 minutes, 5 minutes? I cannot hear. How much time do I have?
Sorry, 13 minutes left.
3?
You have 13 minutes. 13 minutes.
Oh, I thought I need to leave 10 minutes for the questions. Okay.
No, yeah. Sure. That's included. Yeah.
Okay, in total. Okay, so okay, I'll talk for 4 more minutes. Okay. Then we have okay. So what I wanted to say here, that unless the mass term dominates, which it doesn't, if we assume the scaling that m squared is smaller than square root of lambda, this quantum mechanical problem, this Schrödinger problem, has to be solved numerically. Okay, that's where the strong coupling went into. But that's okay. Just one quantum mechanical problem, you put it mathematically, you find the spectrum. And then once you have these eigenvalues, you can find, say, you basically solve the problem for one-point probability distribution. There is a ground state, which is static. That's a very well-known formula, distribution of the field. It has this sort of thermal form, e to the minus v over h to the 4. And then to find a two-point distribution, we solve this a little bit more complicated equation. Again, it's a quantum mechanical problem. You can set up a sort of sudden perturbation theory for this perturbing operator gamma. And again, everything works. Okay, I don't want to get stuck on this. A higher point function, they have conformal form, and that is a sign of de Sitter invariance, which is preserved. Okay, I summarize the technical part. We derived an effective field theory-like description for long modes. It's given in terms of hierarchical structure of system of partial differential equation. And expansion is organized in the number of space-time points in which we fix the field. Okay, so if you want like an n-point correlation function, complexity of your calculation grows with n. Okay. And if you want to go to higher order in lambda, you also need to include correlation functions with higher n in your partial differential, in your procedure. Okay, a few more comments. Non-equal time correlators can be computed in a similar way. All correlators in the setup are de Sitter invariant, and importantly, decay at late times and at large separations. And this shows that at late times, correlators are state dependent. Basically, if for states, it is created by small perturbations of the state that I consider, because we can consider states that are being created by acting of operators at some fixed time on our Bunch-Davis state. And then if we compute correlation function in this new state at late times, it will be independent of this operators. Okay, so that shows kind of the attractor nature of the Bunch-Davis. Okay, as I said, that the very leading equation it agrees with Starobinsky stochastic operator, but nothing is stochastic. We're just carefully taking a path integral in quantum field theory, right? And then we computed, for example, the explicit form of subleading corrections in lambda. Okay, if someone cares what this, I can say it, but you're still getting some Schrodinger like operator more complicated. You can use quantum mechanical perturbation theory to find this again. Okay, let me fast forward because these are things that I was expected I wouldn't have time to say. But I wanted to just one last slide on gravitational backreaction and inflation. So the formula still applies. Long wavelengths matter and metric and inflaton perturbations. So they can have large amplitude, but they carry little energy. Okay, and one may worry that there is no potential, say for graviton or for inflatons, so there is no steady state. But this is not a problem because I didn't show you in my slides, but the equations, I can show. I mean, equations can be also solved. They describe time evolution. They can be solved for non-equilibrium states. And this is what happens for slow roll inflation. There is no steady state of the inflaton field. At least it doesn't reach it before the end of inflation. But that's okay because the inflation, at least before it becomes eternal, there is some bound of how long it can take time. So there is some slowly evolving state that we can still use our equations to take care of, and nothing is divergent, and back reaction never becomes large and is fully under control. Let me stop here. Okay, there are these are my conclusions, but it's basically what I just said. So let me take some questions. Time for them.
Okay, thank you, Victor. So, do we have any questions? We have at least Syksy has a hand up. And Andrei. Okay, so maybe we start with Syksy.
Yes, thank you for the talk. Can your formalism recover these finite time effects? So if you look at, for example, the summation of the leading logarithms in lambda phi to the fourth without the mass term, then you have this time-dependent shift, which comes from the competition between the stochastic effects and the classical force, and which then finally reaches an equilibrium state.
Yes, although, okay, what I should say is the following, that, okay, so let me say two things. So I took mass finite, just to make it in a sense more general. If I set mass, say 3-level mass to 0 in all this computation, everything works, okay? There is nothing special about like setting mass to 0, okay? So the regime that you say, the theory that you say is included. Now, as I also said, we can study non-equilibrium states. So we can start with some states, I don't know, maybe that you want in perturbation theory, maybe free theory, Bunch-Davis vacuum, and see how it evolves to the state that I say is the equilibrium one, which is, you know, the Bunch-Davis vacuum of interacting theory. And the formulas will work. The only thing is that the formalism is kind of complementary to perturbation theory. So, you know, while perturbation theory works, this will be very inefficient. You will have to work very hard. This formalism becomes very efficient at later times, okay? When the logarithms become large, so when we wait a little bit, we get closer to this my state, then yeah, the formalism becomes very efficient. And it's true. It captures the effect of resumming. The problem is that I don't think that anybody managed to efficiently resum these logarithms in perturbation theory, in lambda phi to the 4th theory.
But
it's
lambda,
the latest
lambda,
I know it worked by Raman, Sundrum, and Matthew Baumgart. They resummed something, but they didn't get very far. I think not far.
No,
you know,
no. I think in lambda phi to the 4th, these leading logarithms have been resummed and showed that this.
Maybe leading logs, maybe yeah, maybe okay. Depends
leading logs,
what
yes.
say sub-leading. Okay, leading logs. Yeah, okay. It works. It agrees with the thing I'm familiar with by Raman. Yeah, there is some leading logs for 1-point function, I think, which is true. It exists. Here I was more focusing on 2-point function, which is a more non-trivial observable. I think it's probably possible. Maybe one more thing. Since you asked, I add this thing. So we also did some calculations, and other people also worked on it in large N theories, where it's easier to resum. So you can, for large N, you can resum for any lambda. Okay. It's easier to identify a set of diagrams, and then it agrees. So here I have this draw here, I say 1 over n and lambda. In my approach, I'm still perturbative of lambda, but I can do it for any n. This is the red regime. And then in large n, we can do, we need large n, but we can do it for any lambda. And then here, when they overlap, they agree with computers. This lambda s is the exponent that governs the decay of the 2-point function of the singlet in the OM sense operator. And okay, you can compute it, you get something in the square root of lambda. Then there is a sub-leading term that I mentioned that is linear in lambda. And both of these terms agree with large N calculation, which is diagrammatic resummation. So that may be also at least in the case where I understand well how to resum diagrams, they agree. But if someone understands how to do it for n equal 1, then it will also agree.
Thank you.
Okay, so Andrei, did you get your question answered?
Yeah, I got an answer to my question. Thanks.
Okay, so then Misha.
Yeah, hi Victor. Thank you for the talk. So, do I understand correctly that what you do doesn't depend on number of space-time dimensions?
Yes, it's very, I didn't say it, but this IR de Sitter physics is really independent of the number of dimensions, because you see, if we go to higher dimensions in flat space, IR divergences become weaker. But in de Sitter, the propagator of a light fields, it behaves like 1 over k to the d minus 1 in any number of dimensions. So the momentum integrals are always equally IR divergent, say in 2D or in 10D or in whatever.
I see. And well, a related question. You are not responsible for that, I guess. But what was the reason to say for Polyakov and others that odd dimensions are bad? And so, what was the difference between?
I can explain you in private what I think. I know what they're doing wrong, but okay, let's not put it on the recording.
Okay, thank you.
They compute a bubble diagram, and in odd dimensions, they get some strange result. I would say that I disagree with.
Thank you.
So, Sebastian?
Yeah, thanks a lot for the talk. Can you say a bit more how you would include gravity? So in particular, how you would approach the question of the back reaction on the background?
Yeah, okay, so I should say that, okay, I wouldn't have time to talk about gravity anyway, but then since we haven't written a paper, Leonardo asked me not to put too many equations because he's worried that if I start giving talks about it, then I will never write the paper. But the thing is that, look, you do this, you start, you say, okay, you have some, I know, you say we are in inflation. You take your Lagrangian of EFT of inflation. I don't know what you have single field, mild field, you know, you pick your theory and you do the same thing as we're doing, okay? You have a more complicated action, you do all the same steps, you insert these delta functions, you know, steps I had in the beginning of the talk, you turn the crank and you derive these equations for this this type of equations that now depend on say inflaton field and metric field and maybe some other field that you have in your EFT of inflation, just some more complicated equations, and then these terms will be exactly the same. This term will be exactly the same. The only kind of difference will be that for the for inflaton we will want to ignore its potential, right? So there is none of this term. So the eigenvalue problem becomes such that you don't have like a steady state. It's like, quantum mechanics, but one direction is exactly flat, right? So you have like more like plane waves in this direction. That's your eigenfunction. But that's okay. You still proceed. You look at this time evolution, and then okay, you assume some initial conditions for inflation. Again, that's a problem we're not addressing here. We assume that inflaton field starts somewhere and that the modes, other modes are in the Bunch-Davis vacuum, and then you evolve it and then you solve it. And then in perturbation theory, we get logs after some time in your loops, but here these logs are resummed in the same way as they are in just lambda phi to the 4 theory. So there's no conceptual difference. The only technical complication that you are not expanding about some steady state, you're expanding about some quasi-steady state that is classical rolling on inflaton plus some spreading. As intuitively was understood by people, a long time ago, saying in this paper that I cite here, all right, okay, little, I mean, you probably know this paper, this by Paul, Sergey, and others, Leonardo also, that, if the spreading starts to dominate classical rolling, then you go into eternal inflation regime, which means, but say before we go to, and we can discuss eternal inflation regime if you want, but in this now I didn't want to discuss, before we go to that regime, everything is under same level of perturbative control as it is without gravity, which is a full control. Okay.
Okay. So,
yeah, thanks.
We'll write a paper at some point, it's slow, and then it will be explicit, but yeah, conceptually.
So thank you, Victor, for this interesting talk. Indeed. It's time to move on, however. So is Enrico ready? Right? Yeah, thank you. So is Enrico ready already? Taking over? Yep. All right, so you can take over. So next talk is Enrico Pajer.
Could you give me Pajer, yeah, that's great. Could you give my iPad the sharing thing? It should be called.
Yes, how it is called?
Yeah, it's called iPad.
Enrico's iPad, yes.
Enrico's iPad, thanks.
Yes.
Right. So Enrico is going to talk about bootstrapping large Graviton non-Gaussianities. So whenever you are ready.
Okay, well, thank you very much for the invitation and the opportunity to present my work. Yeah, so see, this works. You can all see this. Yes, good. Okay, well, the idea is to take a different approach to the way we usually compute observables from the primordial universe in cosmology. So we are living here on this line, time is running vertically, and we see something. Fortunately, so far it's not been that much, but at least we have seen something, a 2-point function of primordial scalars. And what we would like to do is what we do in science in general, to use this to make some predictions for the next thing that we would like to see. Some endpoint function of scalars, maybe some 2, 3, 4-point function of gravitons. So that's the goal. The way people have approached this problem in the past 20 to 30 years is that they have tried to build models that describe the time evolution that indeed match the 2-point function that we have observed. And in writing down these models that usually require a Lagrangian and are computed perturbatively, they have assumed some principles. If these are quantum field theory models, they should obey unitarity, so the predictions are physical. They obey locality. They have all the symmetries that make the problem tractable, as well as all symmetries that are observed, such as homogeneity, isotropy, and almost scale invariant. And then, at least in perturbation theory, given a model, you sit down and compute some observable, make a prediction, and then you do it all over again for another model. The idea of this talk and of a series of developments in the past 2 or 3 years is how far can we go in making prediction for this observable without having to actually write down the model and compute for that model. Of course, we're going to use the same input, which is we will have to obey some fundamental principles such as unitarity and locality. And you might hope, which is what happens both for amplitudes in particle physics or for correlators in conformal field theory, that as long as the observable you want to compute is simple enough, probably a lot of the answer is completely fixed by these principles without the need to write down models. And many models will give you the same result because that result is the only thing that is self-consistent. Great examples are present in any, for example, in 3-point amplitudes that are fully fixed by symmetries, and you can write infinitely many Lagrangian, but the result can be one and only one. Same happens for cosmology. So that's the main goal of what I'm going to do in the next 30 minutes. I'll just give you a couple of motivations and then give you the main idea of what the calculational tool is. If we don't write a model, what do we do? And the main tools will be using unitarity to get as much mileage as possible. And to make it all a little bit more concrete, since I'll have some very, very, very general results, I wanted to give you one example which displays how useful this approach is. And this particular example for this talk is going to be Graviton 3-point functions. There are many other examples that have been discussed, but it's good to focus on one. And I think this is particularly interesting, both because it's of phenomenological relevance and because the result had not been computed with standard methods anywhere in the past, and is particularly simple nevertheless. Okay, just one slide of motivations, which is probably not so needed, but it's good to remind ourselves why some of us like cosmology, is because we think that by measuring very low scale, super long wavelengths, fluctuations, distribution of galaxies, we are actually probing quantum field theory in curved space-time, and at least the perturbative regime of quantum gravity. We should be inside this object. So we measure something, we average it over the sky, and at least on large scales, there is a very straightforward linear transformation that we fully know, and that relates this to a quantum field theory correlator. So if you have anything interesting to say about quantum field theory correlators in quasi-de Sitter space, then you can give some interesting information to the study of cosmology. Okay, so for me, the goal of primordial cosmology, understanding this object as well as we can, some expectation value of the product of fields in the asymptotic future of the Sitter space or quasi-de Sitter space. This object in principle has a lot of information, should also include information about the UV completion of gravity to some extent. Okay, so the aspiration, of course, is the usual one. We want to learn about new degrees of freedom and their interactions. We want to test the laws of gravity at different energy scales. These are going to be much shorter distances than what we have ever tested. We even want to discuss whether there is some obstructions to do quantum field theory in the Sitter. Victor already discussed perhaps the absence of some obstructions from the issue of IR divergences, but in general, what is the set of theories that are consistent in the Sitter, and perhaps more ambitiously, is there any quantum theory of gravity which admits de Sitter asymptotics? Can we develop some kind of holographic or string theory approach? So these are the long-term aspirations. To get there, I will start deriving some results within the regime that we understand, which is the perturbative regime. Okay, so the most important thing is to discuss what we actually measure. So I'll spend some time on that. So when you want to bootstrap something, you have to really think hard of what it is that you measure and which consistency requirement it has to obey. So let's discuss the observables, although Victor already mentioned them and they have been already implicitly mentioned in this conference. So I'm going to assume throughout that the very early universe is well modeled by at least half of the Poincaré, half of the Penrose diagram of de Sitter space, which is also called the Poincaré patch. In the Penrose diagram, this green line represents the infinite past, where I'm going to assume that some initial state is present, which is which matches the vacuum state in Minkowski, which I call the Bunch-Davies initial state, and so it is described by some wave function or wave functional of all the fields in the system. And then what I would like to know is what is the final state of the universe in the asymptotic future. If you want this, you can think of it as the future conformal boundary of de Sitter from a mathematical point of view, or from a physical point of view as the reheating surface at the end of inflation. And so we would like to know what is the state of the universe at that moment. That's what then will be used to match to observations of large-scale structures and the microwave background. Okay, so we're going to describe the universe using its wave functional, which is a function of all the fields in the system, including standard model, graviton, inflaton, and whatever else. And we're going to write it, we're going to Taylor expand the log of the wave function, and it has some arbitrary Taylor coefficient that I call psi n. And if I give you all of this psi n, I tell you the full state of the system. Then, at least in perturbation theory, and as long as this converges, you can compute any expectation value you want with the usual quantum mechanics rule, psi star or psi. Often when people do cosmology, they talk about correlation functions, but at least in perturbation theory, these are closely related to these wave function coefficients, psi2, psi3, psi4. For example, psi2 is related to the 2-point function, psi3 is related to the 3-point function, and so on and so forth. So the rest of the talk will be about these psi-n's, but at least in perturbation theory, you can always go back and forth from these and the correlation functions that are measured. Okay, well, this could be in principle. So how do we compute this wave function? Well, just like we do in quantum mechanics, we can write it down as a path integral from the infinite past, in which we set some initial state that we set as Bunch-Davies to some final configurations in the future boundary, and we weigh this path integral as e to the is, where s is some action. Now, if you give me a theory, I can sit down and compute this in perturbation theory. So in principle, this could be the end of the talk. The way we actually compute this is we can write down Feynman rules to compute perturbatively these wave functions. There's slightly different Feynman rules, but they have the same flavors. Every time you have an internal line, you have an internal propagator that I call G. An external line has a back-to-boundary propagator that I call K. And every time all of these lines meet at a point, that's a vertex of the theory. And that depends on the interactions that you have written down in your theory. So in principle, this is the end of, you could sit down and compute, but there are many difficulties in doing this. Even at tree level, you have, for a diagram with V vertices, you have to compute V nested time integrals. In general, you completely lose track of what were the consequences of general principles such as locality and unitarity in the final results. And even very simple results, they become quickly intractable from this approach. But without mentioning all the degeneracies from field redefinition and gauge artifacts that could arise from this way of computing. So we would like to do the calculation in another way that doesn't require actually computing this bulk path integral. And so to do that, the first idea is just to use symmetries to simplify our life, as we always do. Clearly, we're going to start with all the observed symmetries: homogeneity, isotropy, and scale invariance. We have seen them in all primordial fluctuations. So scale invariance is only approximate up to corrections of a few %, but I'm going to treat it as exact for this talk. And so that's the starting point. Then you can ask, well, shall I add more symmetries or shall I stick with only the observed one? Both are good ideas. If you add more symmetries, you only get a subset of the possible models, but probably you can get more mileage and more general results. If you stick with the observed symmetries, perhaps you get something which is phenomenologically more relevant, but you have to work a little harder. So both approach. So if you add more symmetries, there is a theorem that the only thing you can add is a de Sitter boost. So enlarge this set of 7 isometries to 10 of them, which corresponds to the isometry group of the Sitter space. If you don't, you only keep this and nothing else. Let's give an example of why these symmetries help. The 3-point function of gravitons. You could write down and sit down and write down all kinds of cubic couplings with Riemanns and derivatives acting on Riemann, and you could, for each one of them, compute the 3-point function of gravitons, and you would always only find 1 of 2 results, or 0, and these 2 are the only 2 results that are compatible with the Sitter invariance. So Maldacena and Pimentel already more than 10 years ago showed that the 3-point function, it doesn't matter which model you compute it from, it can only be one of these 2 functions because these are the only 2 3-point functions of gravitons that have the correct de Sitter isometries. So this result is fully non-perturbative, is only based on isometries. And these symbols here are spinor-helicity variables that have been adapted to the cosmological context. But this is just a function of the kinematics, which are the external momenta, K1, K2, and K3. So this is very interesting. Actually, there are three wave function coefficient, but only 2 bispectra that can be measured. So this is very interesting. However, we would like to extend this to something more realistic. And in realistic models, we know that the Sitter boosts are always broken, and in general can be broken by a large amount by the inflaton background. The reason is that we know that the Sitter has to end, so there is an inflaton which is counting time and at some point says stop, inflation is over, and that foliation of space-time, which gives us a clock, breaks boost in general, and that breaking can be large. So in realistic models, we cannot rely on the Sitter boost, and these results have to be generalized to allow for the absence of the Sitter boost. So for the rest of the talk, I'll try to show you how much of that can be done. We will have to work harder. So here, assuming the Sitter invariance, we could do the whole thing non-perturbative. Without boost, it's more realistic, but I'll have to work harder and bring in some other physical principles, and in particular, I will bring in unitarity. So for the rest of the talk, I'll assume translations, rotations, and dilations, but nothing about the Sitter boost. In fact, in the scalar sector, there is even a theorem that says that you have to give up the Sitter boost if you want to get anything that is measurable at late times in single field inflation. So this is a very interesting thing to do. Okay, so I'm going to bring in 2 additional tools beyond symmetry, which are a little bit more physical than symmetry. One is locality and the other is unitarity. Let me discuss them in turn. Okay, so locality, so colloquially, this is just the idea that what happens far away doesn't affect what happens here. In flat space, it's very clear. We usually have the notion of cluster decomposition that tells us that correlation functions have to factorize into the product of correlation functions as we move the points far away from each other. To some extent, there is no notion of cluster decomposition in the Sitter because no matter how far 2 points are at late times, if you evolve them back in time, there is always a time for which they were very nearby. So their correlation functions does not have to decay like a power law. And for example, for massless field, it would be more like a logarithm. So there is not a good notion of locality. So instead of using that more physical notions of locality, we're going to use the more practical notion of locality that we always use when we write down models, which is the notion of manifest locality. It means we have in mind of writing down Lagrangians in which different operators, different fields can only interact at the same space-time point. We can have derivative of the fields, but only a finite number of them, not infinitely many. So this is the notion that I will call manifest locality. So for massless fields and massless gravitons, which are the most interesting things to study because they are the only ones that survive at the future conformal boundary of the sitter and therefore can be measured, there is a very simple relation that enforces manifest locality. It is a necessary condition for a wave function coefficient psi-n to come from a manifestly local theory of a massless scalar or graviton. And it is that if you Taylor expand this in the norm of the external vectors, k1, k2, k3, the Taylor expansion cannot have a linear term. So d psi and dk at k equals 0 has to be 0. Very simple and very useful. So this will be one of the leading terms. Notice that I never have to talk about the time evolution or locality in the bulk. This is just a statement about the observable itself. I'm going to call this the manifestly local test for lack of a better name. So any interactions that you could have, whether it's Lorentz invariant, the sitter invariant or not, doesn't matter as long as it is the product of fields and their derivative at the same point. You sit down, you compute, and you will always satisfy that constraint that I've written down. Even though it is less obvious, this actually is also true for general relativity, for pure gravity after you solve the constraints. So let's see how this simple set of rules is already enough to perform a calculation, and then I'll add one more rule, which is unitarity. But for the moment, let's not invoke unitarity yet. So I claim that the three-point function of scalars, which is perhaps the simplest possible observable that you can think of, and it is non-trivial because we don't have full de Sitter isometries. And in fact, it's the main thing that people are looking for in the CMB or in large-scale structures, can be directly computed in 2 lines, given this what we said so far. So first of all, let's apply all possible things that we know about this three-point function. First of all, we know we are working at 3 levels in the sitter, and therefore this has to be a rational function. So a polynomial divided by a polynomial. Scaling variance tells me that whatever the scaling of the polynomials upstairs, it has to be three more than the scaling of the polynomial downstairs. So I get scaling variant results. So this polynomial is of degree 3 plus p, and below is a polynomial of degree p. Then I know the variables. If I have 3 fields that are identical, as it is relevant for observations, since I'm always measuring the same field in the sky, for scalar perturbations, this polynomial has to be written in terms of symmetric combinations of the momenta, k1, k2, k3. And there is a theorem that says that these are the 3 variables that you can use. They're called the elementary symmetric polynomial. Finally, I'm going to use the Bunch-Davies vacuum plus locality. They tell me that the denominator can only have 1 and 1 pole. The only pole that is allowed is when the sum of k1 plus k2 plus k3 vanishes. So that the denominator can only be kt to some power. No other polynomial is allowed, otherwise they would have different poles. So now the problem of computing a three-point function has been reduced to the simpler problem of computing a few numerical coefficients in a polynomial of a given order. Much simpler. It is easy to solve for the value of this numerical coefficient by ordering p. So I'm going to assume that p represents the effective field theory expansion in the number of derivatives. The larger p is, the more derivatives I have in my effective field theory description of the system. So it makes sense to start solving for p equals 0, 1, 2, 3, and so on. And we have derived solutions for any p. But just to show you how it works, you write down psi3, it's a polynomial with unknown coefficient cn's divided by kt to some power. The order of the polynomial is 3 plus p. And then you impose locality in the form of this test, that the derivative with respect to k at k equals 0 has to vanish. And that gives you all and precisely all solutions that can be obtained writing down a model. And we have proven this by counting how many solutions this equation have and counting how many effective Lagrangian you can write down, up to field redefinitions and integration by parts, and the number matches. So this is much simpler. It's just one equation, and then order by order you solve it. And the solutions look like something that you kind of know. For p equals 0, there are two solutions. One has the log and the other no. These are so-called local and conformal non-Gaussianities. For p equals 1, there is no solution. For p equals 2, there is one solution. P equals 3, another solution. These solutions were known in the literature. They go under the name of equilateral and orthogonal non-Gaussianity, and they've been extensively studied and looked for in the CMB. What this method gives you, though, is an infinite set of solutions for p equals 4, 5, 6, 7. Those correspond to higher derivative operators, but they are still possible signals that that could emerge bearing some issues of naturalness. Okay, so surprisingly, we are able to compute even if we don't have a model. Okay, just because there are only very few functions that satisfy all of the constraints that we are imposing on them. Okay, the three-point function is a very simple object. It can only take so many forms. To get the three-point function of gravitons, we need one more ingredient, which is unitarity, which we haven't discussed yet. So colloquially, this is just the idea that probability has to be between 0 and 1 for the theory to make sense. And in quantum mechanics, this boils down to the constraints that time evolution has to be implemented by a unitary operator in the Hilbert space, so that norms and therefore probabilities are conserved. And the consequences of this very simple assumption, u dagger equals 1 for the time evolution operator in cosmology, were not known. So if till 2 years ago, if I gave you either a correlator or a wave function coefficient and I asked you, does it come from a unitary theory? I don't know. The only way was to do the calculation again and check that the theory you started from was actually unitary. Luckily, we have a better tool now to decide whether something comes from a unitary theory and therefore to use that as a bootstrap tool. In particular, consider the simplest possible interactions in which you only interact once. In fact, you can have n fields interacting. It doesn't have to be 3, any number, as long as they interact only once. Then it's easy to prove in perturbation theory that the nth wave function coefficient satisfies this very simple relation, psi n plus psi n star, where its argument get the minus, both every vector get a minus, and every energy, which is the norm of a vector, also gets a minus. So it's analytically continued to being minus k. This very simple combination has to vanish. This is a simple property to satisfy in the free theory, and unitary evolution preserves this property in the interacting theory order by order in perturbation theory. Since this particular combination psi plus psi star of minus k will appear all over the place, we give it a name, we call it the discontinuity of psi n. So I don't have to write this again and again. Okay, so unitary time evolution requires that the discontinuity of psi n for contact diagrams vanish. What happens for more complicated diagrams? Well, we know the result, 2 all orders in perturbation theory, any number of loops. Let's see the next simplest one. There is one exchange, then the discontinuity of this is equal to, you sum over all possible ways of cutting internal lines. There is only one internal line, so only one way to cut it. Cutting it means that you cut it in 2 and push it to the boundary and add a factor of the power spectrum for every cut line. And then you multiply the discontinuity of every disconnected diagram that results from this procedure. This is somewhat reminiscent of Katkowski's cutting rules for amplitude in flat space, but it is actually a different set of rules. Then this and this have to be equal. This very simple rule, we have proven, extends to all orders in perturbation theory, any number of loops. What's beautiful about it is that it is much more general than the sitter, and in fact is valid in any FLRW as long as it admits a Bunch-Davis initial state. is valid for fields of any mass, any spin, arbitrary interactions. So at the practical level, is a very powerful and useful tool. And to conclude this talk, I just wanted to show you how it is useful. In fact, it is useful for a very long list of things. Probably the most interesting and ambitious one is going to be to prove some positivity of effective field theories, but I'm not going to discuss that here. Another thing that it is useful for is that I can give you a 3-point function, and from that you can deduce what the 4-point function is, because it has to cut into the 3-point function. And so you can compute more complicated objects from simpler ones, which is a general feature of unitarity in perturbation theory. It relates higher order things to lower order things. You can compute loop diagrams from 3-level diagrams. And all of this has been done to some extent, but I don't have time to discuss all of that. So I'll give you another example of why this is useful. The example is going to be parity odd correlators. So let's suppose you want to compute a correlator. Is this formula we said before, is the integral, is the boundary path integral in d phi of the wave function squared times whatever the operator is. So to leading order, this is just the psi n plus psi n star coefficient of the wave function. This is the simplest contribution. And because here there was a star on the phi's, there is a minus sign on the momentum. Okay, so this is a contribution. For example, at 3-level for the bispectrum, this is the only contribution that comes. Now notice that this combination that appears here is actually very similar to the one that is fixed by unitarity. The only difference is that there is a minus in the energy. That's the only difference. So this tells us that any wave function term that is even, when you, in k, if you put k into minus k, it doesn't change, that it can never generate a correlation function. It's there in the wave function, but it's not there in the correlator. So that's a very powerful result. For example, let's see how this, well, since time is running away, I'm going to show you directly the Graviton 3-point function. Okay, and let's consider the 3-point function that is parity odd. If it is parity odd, it needs an odd number of derivatives, either 1 or 3, or 5 or 7. Let's say it's 1. And then we write down the most generic terms that can appear, but keeping the correct scaling. The correct scaling by scaling variance is that it has to scale like k cubed. Since I already have 1k here, the rational function is only a rational function of overall scaling 2. So 2 plus p divided by p. This thing is even when you put k into minus k. So no matter what it is, you can spend your life computing it, but you will not contribute to the correlator. The same is for this term too, and the same for this term too. So you can easily see that because of unitarity, all of these terms that appear here, even though they appear in the wave function, they disappear, they cancel out in the correlator. And as a result, there is only 2 terms that survive, this and this, that can appear in the correlator. And the first one that has only a number as a coefficient, and the other one has a second order polynomial, and there is only 2 of them that you can write down that have the right properties. And so we come to the surprising conclusion that there are only 3 possible parity odd Graviton 3-point functions, which is a remarkable result. So more explicitly, let's focus on one particular choice of helicity, let's say plus, 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 but you can compute all other helicities. Then the full wave function coefficient has some polarization tensor contracted with vectors, and then a polynomial in the energies.
30 minutes, Enrico. That was a 30-minute mark.
30 minutes, yeah, I should be done in less than 5 minutes. That's good.
Okay, good.
And then we were able to compute these 3-point functions at 3-level to all ordering derivatives, both the parity even and the parity odd. I'm going to show you only the parity odd because I don't have much time, but in the paper we also compute the parity even to all ordering derivatives. There is an overall factor which is fixed by the little group scaling, like in flat space, and it can be written in terms of spin-or-helicity variables that I have not introduced, but okay, you can look it up, or you can just write it in terms of polarization tensors if you prefer. And then it can be written as a certain polynomials that come from converting polarization tensors into spin-or-helicity variables and can be computed once and for all. This is the list. There is only 7 of them. And then a trim wave function. This is the wave function that has to satisfy the manifestly local test. So we apply the manifestly local test, and we show that there are only 3 results that satisfy 2 all ordering derivatives. And these are the 3, 1, 2, and 3. So I know this is a bit technical, but let me repeat why it is remarkable. If you had written down a model, you could have written down any contractions of Riemann tensors and any number of derivatives with 1 epsilon. And each one of them, in principle, could have given you a parity odd Graviton 3-point function. So naively, you would expect that there are infinitely many of them, higher and higher ordering derivatives. In fact, unitarity says that there are not infinitely many of them, but there are only 3. And you don't need to compute them in a model, but they're fully fixed by unitarity plus symmetries plus locality. And these are the 3 functions. They're relatively simple. They have the polarization tensors in front, and then a specific polynomial that has to satisfy the locality condition at pyramid. Nothing else. So this is a very predictive setup. It's only valid at 3 level, but that's a great target for searches of parity violations in the tensor sector. If we ever are so lucky to see tensors, then this is probably one of the type of non-Gaussianity that we should look for first, because it's so predictive. There are only 3 of them. The same happens for parity odd cross correlators, in which you have a scalar, and a graviton, or 1 scalar and 2 gravitons. They're all similarly highly constrained by unitarity, and there is only 1 scalar graviton and only 3 scalar graviton, where these are free coefficients, and the polynomials are fixed. You cannot change those. You can only choose the coupling constants. Probably the easiest one to measure experimentally is this one, because you have 2 scalars, and we know scalars have more powers than tensors in our universe. So this should be the first one to look for in the data if we ever see tensors. We actually also wrote down all possible parity even by spectra, and for them, there is no surprise, there are infinitely many. So this very specific thing that there are only 3 is only true for parity odd. Parity even, there are infinitely many. So you go higher and higher in the effective field theory expansion, and you get more and more shapes. So everything I've done so far, I never used time, I never used the Lagrangian, or I never used the model, right? So all of this was happening at the level of the observable itself. You could ask whether this is equivalent to actually write down a model. Can I write down 1 model for each one of these things that I have predicted? And the answer is yes, you can sit down and check. For example, in a large classes of inflationary models known as solid inflation, in which there are 3 scalars, you can show that there is 1 interactions that you can write down for each one of these signals. In fact, there is much more than 1. But it's very degenerate, but you can reproduce any of the signals that I've shown with that theory. In the more minimal set of single field models of inflation, actually only 1 specific linear combination of these shapes can appear, and it is generated by this 3-dimensional Chern-Simon term, which is a very specific interactions that you could write down in a model, and then that model would give you this parity odd tensor by spectra. Let me also mention that this was not known before. People had looked at specific models, but it wasn't known that there were only 3 shapes, and it wasn't known what they were. Okay, I've shown that there is a list of constraints that correlation functions and wave functions have to satisfy at the future conformal boundary of the sitter, and these are very constraining that simple observables, which are actually the one that we care about to measure in the sky, are to some extent fully fixed by these constraints, or they're fixed up to some numerical coupling constants. This is just the beginning. There is a lot more to be done, and I thought I would spend just 30 seconds mentioning what are the ambition of this program. So far, we have shown that it can be used as a concrete calculational tools, but hopefully one can do more and one can start extracting some ultraviolet constraints. So one idea is to derive positivity bounds as they are derived in flat space, leveraging the analytic dependence of an observable on the kinematics, plus unitarity. You usually can put bounds on the low energy Wilsonian coefficients, but no one has been able to do it in curved space-time because those observables are so poorly understood. But using this development, it can be done. And perhaps the other thing I wanted to mention is that in principle, one could have enough constraints to actually develop a numerical bootstrap like it's done in the numerical CFT bootstrap to actually compute or exclude a set of non-perturbative 3-point inflationary bispectra. And I'll stop there. Thank you very much for listening.
Okay, thank you, Enrico, for a very clear talk.
Thanks.
So, do we have any questions? Anybody? Hands up. Anna? Please, Anna, go ahead.
Hello, can you hear me?
Yes.
Yes.
I have a question. Are there any concrete models of inflation which could be ruled out using the bootstrap data, like unitarity constraints or so on? For example, the model predicts that the non-Gaussianity should look in some way which is forbidden by unitarity constraints.
Yeah, that's an excellent question. And so we are not there yet. That's where we want to be, but we are not able. So this unitarity constraint, as long as the model that you have written down was unitary, typically had real coupling constant, then it will satisfy the bounds that we have so far. So from that point of view, it probably, if you wrote down some scalar field theory, it's probably fine. What we want to do now is to see what the consequences of assuming that the full UV completion is unitary are on the effective model. And then there will be some bounds that are highly non-trivial, that are invisible to the effective field theory, but comes from the requirement that the UV completion is unitary and local. Those bounds have not yet been derived, but it is an ambition of this program that within 2 or 3 years, we should be able to have those fully de Sitter positivity bounds. The way to get there is that you need to understand what is the analytic structure of these observables in the kinematics plane, and then use unitarity to say that certain things that you cannot compute that come from the UV have to be positive. So perhaps next year I will be able to give you some answer to your question, but yeah, this is the status of the field.
Okay, thank you for your reply. But do you expect that these bounds would be stronger than those that could be obtained just, for example, taking this scalar field in flat space and getting flat space positivity bounds?
Yes, well, rather than stronger, I would say they would be different and I would say correct. The one that you get in flat space are probably not the correct one to use in de Sitter. So my idea of if you were to draw schematically the set of theories that are consistent in de Sitter and the set of theories that are consistent in Minkowski, I expect a Venn diagram like this. Hopefully you can see it. So not all theories that are consistent in Minkowski are consistent in de Sitter. And I can give explicit examples of, for example, supersymmetric theories. And vice versa. Not all theories that are consistent in de Sitter are consistent in Minkowski. For example, if you take a phi dot cube interactions coupled to dynamical gravity. So I know theories that live here, and I know theories that live there, and I know theories that live here. So I don't think it's correct to use Minkowski positivity bounds. People do it as an approximation, and maybe it's okay because we don't have much better, but I don't think it's the correct answer in general. I can give you some deeper reason of why you cannot take the actual UV limit, the flat space limit in Minkowski. And there are several problems. One is that energy cannot be measured in Minkowski, cannot be measured with an error of order Hubble. And so you can never say whether there is a pole in an amplitude. But okay, I'll leave it at that for the moment.
Right, so we are running out of time. So Victor still, thank you, Anna, for the question. Victor still, maybe one very quick question, very quick answer. If you can do it in a minute, I'll allow you.
Sure, yeah. The question is the following. Say your statement that there are only 3 parity odd amplitudes for gravitons. Is that so far a 3-level statement, or that's like in loops they can also not get generated? What is the status of full non-perturbative?
No, so far it's only 3-level, unfortunately. Only 3-level. Okay. Presumably they come out at loops, so then one has to study, but there is
observation is
no
not so relevant, but conceptually I just wanted to understand. Yeah.
Exactly, yes. Yeah, no, that's the reason. If they were only also forbidden at loops, I would have looked for a much deeper reason, because if they're fully forbidden, there should be something very simple to say. But it's only a 3, I would say it's an accident of 3-level.
Okay, thanks. Yeah,
thanks.
That was
okay. Thanks, Enrico, and thanks for all the questions. It's a good discussion, but we have to move on to the last talk of the session. Mikhail, are you ready?
Yes. Can you hear me?
Mikhail Ivanov, talking about fundamental physics from galaxy survey. So now, are you telling us how these coefficients can be measured? Maybe.
Yes.
Okay.
Exactly.
Up to you.
Thank you. Thank you for this nice introduction. And okay, let me share my screen. Okay. Do you see my slides? Do you see my mouse? Okay, great.
Yes.
Good. Yeah, thank you. Thanks for having me here, and thanks to all the organizers for hosting this great conference. So I'm going to be talking about exactly the measurements, like the possibility to measure signals from this new physics, and some of the things that Enrico just mentioned, regarding non-Gaussianity here. But in general, I want to just start with a brief overview of cosmology and why large-scale structure becomes the leading cosmological probe right now. So over the couple of last decades, using cosmological data, we have created a very coherent and consistent picture of our universe, where it all starts with inflation that could have happened at the when the typical energies were as high as 10 to the 16 GeV, and then inflation creates the seeds for structure formation, and then those seeds later on evolve and become what we see now as CMB and galaxies. So in this picture, CMB is the cosmic microwave background radiation, is the radiation left over from the time when the first atoms were created. And the CMB gives us the very first picture of our universe, and we can see these primordial fluctuations that were generated during inflation. And it's a very important, very first snapshot of our universe. But in principle, later on, we see the same fluctuations evolved in the form of galaxies. And in terms of galaxies, we can also measure their redshift. So we get the full three-dimensional volume of information, we get the full three-dimensional maps. And in this sense, we get many more snapshots of our universe and all these fluctuations. We can use them to understand something about the evolution of our universe and also inflation. And I think that the success of the standard cosmological model and the CDM is that all these snapshots, all the data can be well described with a simple model with just a few ingredients, such as inflation and dark matter being just cold particles, and also the cosmological constant plane, responsible for late time accelerated expansion. And this picture is, of course, very coherent and nice, but we know that there are certain known unknowns, that sort of this picture is incomplete because we don't know what was inflation exactly. We don't know if dark matter is really cold, or if it has one component or multi-component. This we don't know at the moment. And of course, there are many more questions like that. And in general, there are also some possibilities of unknown unknowns. So those are surprises in the data. Those are some anomalies. So we should keep our eyes open and check all the data that we have, and test lambda CDM with all the data, trying to see if if this really a coherent picture and we're not missing anything. So that's why it's very important to keep doing this data analysis and using data from cosmological surveys. In all this picture that I described, the working horse in cosmology has been really the cosmic microwave background radiation, and here you can see the cartoon picture of that created by the Planck collaboration. And we know that CMB represents cosmological CMB represents a fluctuating temperature field, and this field is random and Gaussian. So we characterize it in terms of its correlation functions, the simplest one being the 2-point function, the power spectrum that we compute most of the time in harmonic space, in angular space. So you can see here on the right-hand side, the power spectrum that probably you have seen many times. And I'd like to just point out here that this power spectrum has a very intricate shape. It has a plateau on large scales. It has oscillations on intermediate scales and some sort of exponential damping at small scales. And altogether, so this complicated shape as a function of coordinates, as a function of angles, gives us the information about cosmological parameters. And in particular here, let me start the movie. Here I'm showing you how the shape of the CMB power spectrum responds to a variation of the dark matter density. And this is precisely the effect that we use to derive the strongest constraints, strongest measurement of the dark matter density. And the success of the lambda CDM model is that all this complicated shape can be described with just 6 parameters, which is the density of matter, the density of baryons, the Hubble constant, which is the proxy of the universe age, and then tau, the optical depth of our universe at the time of ionization, and also 2 parameters, AS and NS, that describe the amplitude and the tilt of the primordial power spectrum. So this is the CMB picture that we know very well, and that we use to derive, well, essentially to learn the bulk of our knowledge about cosmology. But in principle, we can also add a large-scale structure to that picture. We can use large-scale structure in the same way. So large-scale structure is the distribution of galaxies on large scales. So this distribution is obviously not random. It depends on cosmology very sensitively. And in terms of statistical properties, we characterize galaxies by introducing the over-density field, delta rho over rho, which is essentially a random stochastic field as well. So this field is nearly Gaussian. So at some regime, it can also be characterized by the 2-point function only, but in principle, it's nonlinear and it has all possible correlations. So we can have, the 2-point function, 3-point function, the bispectrum, and so on and so forth. And again, here I'm stressing that the galaxy distribution, unlike the CMB, is 3-dimensional. So we have much more information, and we can build the power spectrum of galaxies as a function of 3-dimensional wave number. And you can see here the measurements from BOSS, from the BOSS survey on the right. And in principle, the story here is very similar to the CMB, that the shape of the spectrum is some non-trivial function of cosmology. So we can see that it has a turnover, it has some overall slope, it also has the B oscillations, and so on. And we can use all the shape information in principle to to learn something new about cosmology. So this is the key idea of the full shape analysis. So we just compute the correlation functions, 2-point function, 3-point function, and so on of galaxies, and just get all the cosmological parameters from the shape. And this seems like a good idea because CMB and large-scale structure are really complementary, because they probe different scales, they probe different redshifts, and they also probe different physics. And in particular, the galaxy distribution gives you a direct probe matter fluctuations, which is sort of different from what you have in the case of CMB, where primary CMB data is mostly sensitive only to the background dark matter density. And another point that I'd like to make is that large-scale structure, again, provides us with a 3-dimensional volume of information, and in principle contains order of magnitude more information, as counted in the number of Fourier modes than the CMB. So this means that in principle we can have orders of magnitude better cosmology, right? We can translate this into order of magnitude better measurements of cosmological parameters in principle. But the large-scale structured data is more complicated, and this is where I'd like to start discussing, really the problems of this program. So the big problem is that the distribution of galaxies is nonlinear, and you can see that if, for instance, if you take a look at the output of cosmological simulations, you see that on large scale, so for 1,000 megaparsecs, really the distribution of galaxies looks a lot like the CMB. So we have just, sort of random Gaussian patterns of overdensities and underdensities called on hotspots. But as we keep zooming in, we start finding more complicated structures like the filaments and then clusters of galaxies and galaxies. And obviously, all these things are super nonlinear, and it's not obvious that we'll be able to describe them, theoretically. And this fact, this sort of breakdown of linear theory is manifest when we try to fit our galaxy power spectrum data with linear theory. We see that on large scales, the fit seems to be okay, but as we keep to short scales, meaning large wave numbers, we see that the difference between the data and the theory grows. And well, clearly that it's clear that we have a regime where the theory systematic error is much bigger than the statistical error of the data. And so this was a big problem. This was the case already, since the first galaxy surveys 15 years ago. And the standard approach until recently was to focus on observables that are stable with respect to nonlinearities, the so-called redshift space distortions and BEO. So the idea was to discard all the shape information as unreliable and just, sort of pick up parts of the, information, some partial information that is more or less, stable with respect to these nonlinear uncertainties. But this method to analyze the data is, of course, not very optimal because we're losing a lot, and we can do much better. But for that, we have to understand nonlinearities. And essentially, there are two ways to do that. The first way is to run a numerical simulation. So we all know very well about n-body simulations. So n-body in principle is the exact, exact theory, exact model for dark matter clustering. So, and in this case, in this situation, for matter clustering, running a simulation is a really good idea because, we have the EV model, just solve it numerically. And then we know that this description is valid for an unlimited range of scales, essentially. But however, the problem is to put galaxies in that picture because for galaxies, we don't know the EV model, obviously. And in principle, computing galaxies from first principles would require simulating every single star in every single galaxy, and which is, of course, impossible. And right now, the state of the art is to use some ad hoc phenomenological models, hydro simulations, and so on. But people are still arguing, what physics should be included there. And it's not clear if, this program is going to converge to, let's say, 0.1% precision that we'll need in the future. And, despite the fact that, there has been a lot of progress in numerics and, also in machine learning, still the generation of full galaxy simulations is sort of time consuming, and it's virtually impossible to scan over cosmological or astrophysics parameters with this technique. And an alternative to that is to use perturbation theory. Oops. Perturbation theory is, of course, is not as powerful as full n-body simulation in some sense, because you can only apply this on a limited range of scales. At some point, things become fully non-perturbative, and you cannot just use perturbation theory anymore. But on this limited, range of scales where PT applies, we can get, in principle, any precision and accuracy in our calculation as we want. And also it's very fast and cheap, and many calculations can be done just, with pen and with paper and pencil. Also this perturbation theory technique is a very natural framework that allows us to marginalize over all the uncertainties due to galaxy formation, because we know that in the long distance limit, all this galaxy formation physics simplifies and can be captured systematically. So why this large-scale structure description, analytic description is possible? This is thanks to having several scales in the problem with large separation between them. And in particular, if we get back to that picture from simulation, we see that there is one scale of order a few megaparsecs that controls the size of the halo and the physics of galaxy formation. And we know that physics, at scales of this size and like shorter is extremely complicated, and we're not going to have a UV model anytime soon. But however, if we move on to scales larger than this halo size, then actually the distribution of galaxies can be described systematically as an effective fluid. And it's important that this fluid is non-relativistic, because the relativistic effects become important only when we get to the size of the Hubble horizon, which is few gigaparsecs. And this nice scale separation allows us now to describe the galaxy distribution systematically in terms of distance expansion. The most relevant parameter here is going to be the size of the halo over the typical distance between galaxies. And this framework, this idea to take advantage of the separation of scales is known as the effective field theory of large-scale structure. It was put forward something like 10 years ago, and since then there has been a lot of progress, and there were many people working on that, many independent groups. Well, Enrico here made many important contributions. But altogether, I'd like to point out that the idea is the same, but there can be different technical ways to realize that idea. And I myself created a framework called time-slice perturbation theory, which is essentially the path integral formulation of the effective field theory of large-scale structure that allows me to compute all the relevant large-scale structure observables in terms of Feynman diagrams, and in principle get the 0.1% understanding of galaxies that we need to test new physics. So yeah, when we put all these things together, the rules are fixed. We can compute Feynman diagrams and so on, and take into account these nonlinear corrections. So we get all that, and we can perfectly describe the shape of the galaxy power spectrum. And in principle, now we can extend this agreement, and we can compute things at 2-loop, 3-loop orders, and so on. And we can also get the 3-point function, bispectrum, 4-point function, and also compute this at multiple loop orders in principle. The caveat here is that since this is an effective field theory, we have to deal with some nuisance parameters or Wilson coefficients that appear at every given order. So here the situation is very similar to chiral perturbation theory, where you have at every given order new Wilson coefficients that have to be matched to the data, have to be fit from the data. And this is an important caveat, because at some point, of course, we expect that there could be some sort of diminishing returns from that program, but we're not yet there. All right, so why are we sure that EFT is correct? Well, first of all, because from the math point of view, that's the only option. This is the only consistent description of large-scale structure. But also we have done several explicit checks of this approach. In particular, we have participated in a blind simulation challenge, where sort of the idea was to recover the true cosmological parameters from a mock data that was simulated for a very large volume, and with some high fidelity, high resolution simulations. And altogether, yeah, we were able to win this challenge and accurately fit the data to 0.1% precision. And another test that we have done is the EFT at the field level, because of course, with all these nuisance coefficients, you might be worried that some of the success comes simply from overfitting. But these Wilson coefficients, they allow you to fit the amplitudes of fields, but not the phases. And in order to get this more stronger test of the EFT, we can compute the EFT at the field level, starting from some initial distribution of initial conditions. And yeah, we can compute the EFT here and test it against the full simulation, and we can see that the agreement is very good. And essentially, EFT accurately describes voids and also clusters, maybe up to the very dense up to the very dense regions where obviously perturbation theory breaks down. But anyway, we have done all these tests and we're sure that EFT is correct and it fits the data. All right, so with all these things, we have created now a new pipeline to analyze data from galaxy surveys, and this pipeline revolves around the code class PT, which is an extension of the standard Boltzmann code class. So essentially, we have put all these loop calculations in the code, and it takes 0.1 second to calculate something like 50 loop diagrams that are needed to describe the actual data. And right now we have 0.1% accuracy, as we have checked in a blind simulation challenge. And yeah, we have extensive tutorials online, and please check them out on my GitHub page. So when we have this pipeline, we apply this to the data, which was the data from the BOSS survey, the Baryon Acoustic Oscillation Spectroscopic Survey. And once we have fit the data, we found these posterior contours on the right. Here I am also showing the posterior contours from Planck 2018, which is the state-of-the-art measurements of cosmological parameters. And here, I guess, yeah, there are 2 points that one can mention. The first one is that the error bars turn out to be very competitive. So it turns out that the galaxy distribution can measure H0 and omega matter with precision very much similar to the one of Planck. And I guess the second important point is that these contours, they sit more or less on top of each other. So we don't see any strong tension, which is a good consistency check of lambda CDM. So we don't see any anomaly yet. Maybe there is one interesting tension that is visible here from this plot, is in the measurement of this parameter sigma 8, which is the late time clustering amplitude. Well, this is essentially the amplitude of the matter power spectrum at scale 8 megaparsecs over H. And you can see that there is some sort of 1.5 to sigma tension between Planck and sigma 8. And I think, so this tension is of course not very significant, but it's interesting because it has been observed independently in other surveys. And I think that it might be actually related to some sort of new physics. So I don't have time to discuss this tension here, but please ask me questions after my talk about the growth tension. All right, so we have done this analysis for lambda CDM, but of course with the EFT, we can compute things analytically also for beyond lambda CDM models, and we can efficiently explore all these different scenarios. And we have explored many models that some of them I'm showing here in this list. But for the rest of my talk, let me focus on 3 particular interesting scenarios, which is early dark energy, that is sort of a model addressing the so-called Hubble tension, then some implications for dark matter, and finally, I will show how to use galaxies to measure primordial non-Gaussianity. So let's start off with a Hubble tension. So as you probably well know, there is a discrepancy between the measurements of the Hubble constant from the so-called indirect probes, like CMB and large-scale structure, that need to assume a cosmological model from the beginning to the end, and like extract H0 from a combined feed to the data. You can see these probes over here in the top part of the plot. And all these, independent indirect measurements, they all sort of scattered around a value of H0 equals 68 kilometers per second per megaparsec. And these measurements are in some tension with the so-called direct measurements that, probe H0 in a late time local universe. And they don't, in principle, they don't need to assume a model. And you can see that most of these measurements, they have sort of large error bars and are consistent with the indirect ones, except for the famous shoes measurements of H0 using the Cepheid calibrated supernovae, which is now in something like a 5 sigma tension with the results of Planck. So I told you before that our measurements, well, it's shown here, our measurement is consistent with Planck, but I think that this tension is very tantalizing, and I guess that many people believe that this is a sign of new physics. Of course, this could be just systematics, but if we assume that this is driven by new physics, okay, let's try to understand what new physics can generate this tension. And in fact, it turns out that it's extremely hard to construct a model that addresses the Hubble tension. And one of the models that used to be successful on the market was the so-called early dark energy model. So the idea is that you can address the Hubble tension by assuming that there was an axion-like particle that acted, the axion-like field that acted like dark energy prior to recombination. So here I'm showing you the profile of the energy density fraction of early dark energy as a function of redshift. So if early dark energy contributed to something like 10% of the total energy of the universe at the redshift, let's say several thousand, then in principle this would be enough to resolve the Hubble tension. So in this new model that in some parameterization has 3 new parameters: the maximal fraction of early dark energy, the redshift where it kicks in, and the initial phase of the field. So in this model with these 3 extra parameters, now you're able to fit the SIMBIT data with, assuming H0 equals 72 kilometers per second per megaparsec, which is consistent with the Schuss measurements. And I think that this is a great success of this model, that at least for the CMB, it's possible to sneak in this new physics there. But however, the problem is that in order to fit the CMB data, you also need to shift other cosmological parameters. And in particular, like physically, because you have this additional accelerated expansion, it washed out gravitational potentials, and you need to compensate for that by cranking up the dark matter density. But if you crank up the dark matter density, this will generate more structure in a late time universe, and this will modulate the matter power spectrum and the galaxy power spectrum. And you can see this modulation over here. It's going to be very, very significant. So here I'm showing the ratio of the power spectrum in the early dark energy model versus the one of lambda CDM. And we can constrain this effect from the data, because in the data, as I pointed out, actually we see some sort of like less structure than predicted by lambda CDM. And altogether, by combining these large-scale structure probes, so Planck and our Bose full shape likelihood, we're able to get a upper bound on the early dark energy that it's less than 5%, which is half of what you need to resolve the Hubble tension. And altogether, the basic early dark energy scenario is in something like 4 sigma tension with the with Schuss. And you can see that here in the plot on the right, that the addition of this full shape measurement is very important to get this strong bound. And just a general remark here is that large-scale structure data in many regards turned out to be very competitive with Planck and with other cosmological probes, and that's why it should be used as a crucial test for models that try to address the Hubble tension, because in many cases people study simply Planck in this regard. And I think that, it's also important to point out that there were many checks that these results are very stable with respect to different analysis choices, and in particular with respect to prior volume effects. All right. So another point, another new physics models that we can try to constrain related to dark matter. So as I said, currently it seems that all the data is consistent with the picture where dark matter is cold, but in principle, what if dark matter is not cold, or at least its fraction is not cold? And these scenarios were able to also test with the galaxy full shape power spectrum data, because the idea here is that in all these situations where some fraction of dark matter is not cold, for instance, part of dark matter, like 3% of dark matter, are ultralight axions, or there is some contribution from light by massive relics. So in all those situations, dark matter has some sort of effective gene scale at which the clustering will be suppressed, and this will be translated into like a suppression in the galaxy distribution. And essentially here you can see the ratio of the power spectra in the, let's say, Axiverse type models, and also models with light relics like Gravitinos. And there we're able to, rule out the shape distortions and get, constraints on these scenarios. And those constraints are stronger than the ones that we're, just getting from the CMB, because, CMB doesn't probe dark matter fluctuations as efficiently as galaxies. All right, and finally, let me say a few words about inflation and non-Gaussianity. So Enrico just already presented the story, and I guess that here I just say that inflation is the mechanism that we use to generate structures, and its biggest success, in my opinion, is that the distribution of the primordial fluctuations, this primordial field zeta, the primordial curvature fluctuation, turns out to be Gaussian, which matches the actual observations. But if there were some interactions, so yeah, this is a result of not having any interactions at all. But if there were some interactions, then of course would generate some distortions in this primordial distribution, would generate, for instance, the 3-point function, 4-point function of zeta, and so on. And this will be very useful to answer many questions that we have about inflation. So of course, one obvious question is what the energy scale. So this one we cannot address with galaxies. For that, we need primordial gravitational waves. But other questions are how many degrees of freedom there were, how fast did they propagate, and if there were any interactions or self-interactions during inflation. And all these questions we can address by studying the primordial non-Gaussianity. So the simplest metric that we can introduce is the overall amplitude of the bispectrum that we call the FNL, but also the shape is important. And as Enrico mentioned, we have, well, essentially 3 important shapes that correspond to sort of different physics. So the bispectrum is a function of 3 wave vectors that form a closed triangle due to momentum conservation. So in this sense, we say that the bispectrum is a function of a triangle. And if the bispectrum sort of peaks at the squeezed triangles, this shape is called local. If it peaks at equilateral triangles, it's called equilateral. If it's peaked on folded triangles, we call it orthogonal. And in principle, this simple like parameterization, just consider these 3 shapes, is enough for many data analysis applications. And it's important that 3 different shapes, they correspond to different physics. For instance, the local non-Gaussianity is typically generated in multi-field models, whereas equilateral and orthogonal non-Gaussianities are some sort of smoking guns or like typical things generated in single field models. And of course, there is the famous Maldacena consistency condition that tells you that the squeezed limit of single field inflation essentially vanishes, which means that if we detect any non-Gaussianity in the squeezed configurations, any local non-Gaussianity, this would sort of automatically rule out single field inflation. So we're
31 minutes to talk now.
Thank
31
you.
minutes.
31 minutes. Okay, good. I'm almost there, like a couple of minutes more maybe. All right. So we have put all these initial bispectrum scenarios in our pipeline, and we're able also to obtain the first constraints on these equilateral shapes from the Bose data. You can see those constraints here on the left, and you can compare them with what we have with Planck 2018. And so right now our constraints are sort of inferior. The error bars are like factor of 6 worse than what we have with Planck. But I think that's important to mention that the very first measurement of constraints on primordial non-Gaussianity from galaxy clustering. So it's a proof of principle that this is possible, that we can control systematics and theoretical uncertainties at the level that we need. And in the future, in principle, we can beat Planck. And for that, we need to get to the 0.1% precision. So first of all, 0.1% precision measurements of the galaxy correlation functions that we'll get with future surveys. And also at this level, we need to control, all the theoretical uncertainties at the 0.1% precision. And for that, it's instrumental to use the EFT because it in principle allows us to get there by, performing the systematic calculations in a distance expansion. And it's important to say that in the future, these limits are going to improve because, well, the limits from CMB are not going to improve much. They're only going to improve at most by a factor of 2 with next generation polarization measurements. So essentially, these error bars are going to stay the same. Whereas with large scale structure, we're able to improve these error bars by a factor of few within the next 5 to 10 years, and therefore soon we'll get the best measurements of the best constraints or measurements of primordial non-Gaussianity from the galaxy clustering. And here, let me just say that we're expecting many surveys to go online in the future. Some of them are already operating, like DESI. Hopefully soon we'll also get Euclid and LSST, Vera Rubin Observatory, and Spherex, and other measurements, and so on. And altogether, we expect all these cosmological parameter measurements that I presented, like H0 measurements, limits on primordial non-Gaussianity. All these things we expect to improve by factor 5-10 in the next 5 to 10 years. So let me summarize my talk. I hope I have convinced you that EFT is a robust analytical tool to describe the distribution of galaxies. And using this tool now, we can extract cosmological parameters from the galaxy distribution data with precision, which is similar to that of the CMB. And also, this gives us many new ways to test beyond the standard model of physics, like dark matter and inflation. And we expect huge improvements in the future from upcoming surveys. And with data from those surveys, many order 1 questions about dark matter, inflation, and gravity will soon be answered. So I guess I'll stop here. Thank you all for your attention.
Okay, thank you. Again, a very nice and clear talk. I see at least one question there from Laura. Go ahead.
Yeah. Yes, thanks. Thanks a lot for your talk. Can you please go back when you discuss early dark energy and the related work?
Yes.
This plot. So, okay, so I'm looking at the plot, and I see these gray bands. They represent some sigma, I guess, around the direct measurements on the local universe. Is that what I'm looking at? Okay.
Yes, that's correct. Yeah, this is the Schro's measurement, essentially. Yeah.
Yeah, and then I'm looking. Okay, then there is the green. So the green is Planck, and Planck is telling me, yes, you can do that. You can really move close to that to the local measurement if you have enough FEDE in this case. And then I see 2 different colors where you include the BAO from BOSS. One is EFT, FS, and then one is standard FS. So my question is, what is FS?
Oh, here FS is full shape.
Full shape. What's that? Can you elaborate on that, please?
Yes, full shape is, so here, indeed, you can see green is Planck, then this blue is using this, RSD and BU, the standard way of doing analyzing the data, like extracting this partial information. So you see that it doesn't help much. Actually, it even gets you, a little closer to H0. But yeah, the red one is our full shape analysis of the galaxy power spectrum, where we do a global fit, like this one. We do a global fit to the data, and we measure all the cosmological parameters directly from the galaxy, from the full shape of the galaxy power spectrum, including here the early dark energy parameter. So we don't use this so-called RSD and BO, we use everything.
I see. And so maybe this is related to my other question, which was at the beginning of the talk. When you say, at the moment, or at least the approach in the last years, it was to throw away the shape. So can you just tell me what you mean with shape in this context? Oh,
here in this context, I mean really the shape of the galaxy power spectrum as a function of K, right? So because we're doing now this global fit that sort of goes for all data points, and this was not the standard practice, because here we're varying all the cosmological parameters like H0, omega matter, and everything. We just extract them directly from the data. This is not the standard way how things were done. So before, people were doing this BIO, which essentially the method was the following: let's assume that my cosmology is given by Planck. Let's calculate some like fiducial, so-called fiducial template, for Planck, and let's try to see if this template can, roughly match the data and constrain like the freedom to move this template horizontally and vertically. That's it. And this was the standard, like the horizontal things correspond to the BU and vertical to the so-called RSD. So you extract essentially like 2 or 3 parameters from all the data, whereas here we do a full global fit and we measure, omega matter, H0, sigma 8, everything. So this is the main difference with respect to the former approaches.
I see. Okay, thanks a lot.
Sure, thank you for your question.
Thank you. So now we are 5 minutes into the coffee break, so I'll give the floor to Inar. So if you have a question, conference organized anyway, if you have a question, it's up to you.
Yeah, very quick question. So Misha, you mentioned that in large-scale structures you have like an order of magnitude more modes than in CMB. But what part of these modes will be available for the EFT approach? Because you can only access mildly nonlinear scales. So what percentage of this 10 times more data will be available to your approach, to EFT approach?
Yeah, that's a really great question. So with EFT, still we'll be able to get orders of magnitude more modes. In principle, let's say there are like 3 orders of magnitude more modes, well, roughly, and like 1.5 orders of magnitude we can get with the EFT.
Okay, cool. Yeah, that was. So, Kima, how shall we proceed?
Yeah, so go ahead. As far as I'm concerned, thanks for all the speakers. I really think they were really very clear and nice talks. I was very bit worried about whether I'm able to handle this chair, because I'm not exactly that's not my strength. But actually, I had several questions that I would have liked to ask, but there was so much discussion that I'd rather let other people go. So thanks for those nice talks and thanks for the discussion. And Inar, maybe you want to say something before we.
Yes, so we can proceed in 2 ways. So either we can ask speakers to join the breakout rooms, and then people can ask questions individually, or maybe we can stay here for a while just to discuss some general questions, maybe. So I know, for example, Enrico was mentioning that. Using this bootstrap approach, you can go to 4-point functions and so on. But from the observational perspectives, this 4-point functions, could they be constraints on them?
Yeah, excellent question. Actually, funny that you asked. Just this past week, there were 2 papers claiming a 3 sigma detection of a parity odd trispectrum of galaxies, which is a 4-point function. So it's a very, very well-timed question. I mean, probably it's still early days, and I think there is a lot that the community has to do to verify these new techniques that they're using. But I think it's an example that there is not a big gap between observations and what theory can compute. So for example, I think that's an interesting example. Most likely it's not going to be primordial, but it would be nice if theories came up and said, okay, this is the set of primordial 4-point functions. I think other examples, I mean, the CMB has put bounds on 4-point functions. So I think just around the bound, one should be able to write down a prediction. There is maybe another fact to mention is that in general, you can turn 4-point functions into 3-point functions by putting a lag on the background. So there is a relation in which if one of the legs has a vacuum expectation value, a 4-point function turns into a 3-point function. So to some extent, studying 4-point function is also a tool to study 3-point function, which are surely firmly within the realm of what we are trying to probe. So those are other examples.
Sorry, Enrico, you say if we are in this regime that you mentioned, that the leading 3-point function comes from just some soft limit of a 4-point function, then doesn't it mean that there is more information in the 4-point function because you kind of, okay, 3-point function is just some particular kinematic configuration of a 3-point function is a particular kinematic configuration of 4-point function. So you kind of cannot lose by measuring a 4-point function. No,
I don't think that all of them.
What's this logic for?
Yeah, the logic is that it's true what I said, but it's also possible to get the 3-point function from putting 2 legs in the background of a 5-point function and 3 legs of a 4-point function and so on and so forth. If that parameter of putting a leg on the background is a small parameter, then you get away with just looking at the 4-point function. But if that is a large parameter, then you have to consider all n-point function and putting n-3 legs on the background, which is not very feasible. And this is precisely what happens with this de Sitter versus broken boost story. When you use de Sitter to compute the 4-point function, at most you can break boost a little bit by putting 1 leg on the background. But the most generic boost breaking 3-point function is much more general than that. And you cannot capture it by putting any finite number of legs on the background. To some extent,
yes,
that's
sure, I understand. I guess what I meant, if there are models, I mean, or at least if there is only at least one model where which we can say close to de Sitter, where the 3-point function really comes from 4-point function with a single leg on the background. Say if we want to test that model.
Yes, for that you're right. Yes. For example, the problem is that there is this general result that tells you that those things are always low-roll suppressed. For example, Maldacena 3-point function does come from putting a leg on the background of a 4-point function. But every time you do that, you pay a price of its low-roll parameters. And so those things are 2 or 3 order of magnitude suppressed with respect to what we are probing now. So all of those are probably... Yeah, even with all the work that Misha is doing, it's still a couple of 100 years in the future, I think, before we can constrain those. On the other hand, when we break boost, we are really trying to get at the boundary of observations. We can get the prediction which is sitting there, as large as you want. The bound is not our ability to compute, but observations, which is why this boostless approach is very useful. It can really compute things that are being constrained now by the data.
Misha, do you have an opinion on this measurements, this parity odd trispectrum?
Oh yeah, this is sure. Yeah,
you're acknowledged in the paper, right? So you're fully responsible.
Right, yeah, they were done by my collaborator, one of them. Yeah, it's true. So there are 2 measurements. One of them, I think, is like something like 7 sigma detection. If you combine all the data, one of them is only 3 sigma. It's like, I guess that Oliver sort of didn't want to push it that much. I feel like, yeah, from the observational point of view, it's like, okay, it's the first time this, 4-point function was measured. And of course, there are many there are many astrophysical, like systematic effects that can generate this. Related to the survey specification and also, to some sort of foregrounds like dust and so on. So right now, I would say that most likely this is going to be just some systematics, but it's nice that people are, looking into that. But from the theory point of view, actually, I had a question to you, Victor, and maybe also to Enrico. Like, if I just, close my eyes and ask what kind of model would produce a, parity violating 4-point function, in terms of the effective field theory of inflation, maybe what would be the model?
I never thought about it. I don't I mean, you can write something down with some interaction with an epsilon symbol, no?
Yeah, possibly something like an axiom, but for instance, the effective field theory of inflation, what would be the order of this operator? Because somehow I feel like if you have this large parity violating 4-point function, you would also get something at the level of the 3-point function, right? And like the EFT of inflation should tell me that like there is a sort of consistency relation between 3-point function and 4-point function for these models.
Yeah, I think it's interesting. We are thinking about it, so I cannot give a very definite answer, but it's not very easy to get something that works and fits the claimed size of the detection. I think it'd be nice to see if there is a model that actually works. Like with, I don't think it's trivial to generate a model. There are quite a few constraints. One of them are the constraints that I presented today from unitarity. Those constraints on the graviton are just the same on the scalar. So if you just work that out, you see already that the simplest thing does not work. But yeah, maybe I'll refrain from saying more.
I also see one hand raised. So Hauri?
Hello, can I?
Yeah, sure.
Yeah, okay. Thank you for the talks. I have a question from Enrico. Imagine that we can calculate all these coefficients until very high n in the wave function that you have given from data. The whole point is how we can do the inverse, which means how can we have a insight about the underlying theory from these coefficients, because this is simply at the end your method look like a very good way of I don't know, fitting the data, for instance. But then how can we go back to the theory and see what is the physics which have created this? This is, I think, a main question that is not really answered neither in bootstrap method nor in effective field theories.
Yeah, so I'll try to give an answer that doesn't bring us into a philosophical discussion, but the scope of physics is to make prediction for something that you can measure. And this approach that I've described does give you a mathematical way to predict a signal that can be measured. Any other thing that you write as a function of time in the bulk, in the sitter, is not something you can measure. The only thing you can measure are the late time correlators. So everything else you say about the system is something you're making up.
Yeah, but in addition, your, especially Bootstrap is based on many assumptions, which is not necessarily, they can be violated by physics. For instance, non-locality, for instance, unitarity even, because considering just simply quantum mechanics, if they are modes that we are not observing, necessarily there is a quantum mixing of the states, and then this can violate unitarity, even if it is not fundamentally violated. Just because of mixing, it can be violated. Therefore, all these things, I don't know really how much this quantification that you have discussed can be really useful for a physical insight to the problem.
Yes, it's an interesting aspect, and I haven't had time to discuss it. But it's true that what we are actually sensitive to is not the wave function, but rather the reduced density matrix that you obtain when you trace out the modes that you don't observe. So in principle, the full calculation would require compute the full density matrix, trace out the mode that we don't observe, and then use the reduced density matrix to predict observable. This can be done. In practice, this gives, in the models that we understand, it makes a small difference, which is higher order. And this is something that can be treated using the Lindblad equation and this open system effective field theory approach, in which you can see that these deviations from unitary evolutions are expected to be small. If you really care to know about how small, I mean, definitely beyond anything we would measure in the future. But from a theoretical point of view, it would be interesting to understand how to treat those two.
And the problem of non-locality, especially because what we usually call background field, for instance, in the both inflation and also quintessence type of models for either modified gravity or dark energy. Again, this is actually a condensate, and these condensates are usually non-local by definition. Therefore, the assumption of non-localities also should be really taken with some grain of salt.
No, yeah, I don't think I agree on that. You can have as many condensates you want as the interactions that take place locally in space-time. So some notion of, if you want to be precise, maybe microcausality, the commutation of operators outside of the light cone. I think that should be satisfied as long as it is a field theory. And if you're talking about UV completion to a string theory, that's maybe another interesting discussion. But as long as you assume that this is a field theory, it should be local in some sense. You don't want things to interact at arbitrary distance.
I mean, even in field theory or even quantum mechanics in the lab, you have, they are very large correlations.
Yeah, but the commutator
you can
is zero.
consider it as somehow non-local.
No, the correlation is not zero, but the commutator is zero. You can measure one and measure the other, or vice versa, gives the same result. If
Yeah, 2-point correlation, yes, is zero, but
as an operator, you can put it in an endpoint function, still zero, the commutator outside of the light cone. I think I'm just doing standard quantum field theory notion of locality. Is the commutator better be zero outside of the light cone, otherwise we can kill our grandfather. I mean, not doing much more than that. So I don't think that having an expectation value violates that.
Yeah, at least, yes. I mean, anyway, if the condensation of of some sort of field is important, I'm not sure that with the bootstrap can have, I mean, find a signature of it. This is what my point.
No, I disagree. All of the fields that I'm discussing can have an arbitrary expectation value, I'm just discussing perturbation on top of that expectation value. So that can be whatever you want. As long as it is homogeneous and isotropic, because those are the symmetry I've chosen, you can have a valve. In particular, these things is really the inflaton. So it has a vacuum expectation value. It's fine. It does not, it's not in contradiction with this notion of locality that I'm using. All the effective field theory of inflation, for example, is included in this treatment.
Okay,
so it's fine to have that, but this can be also used for dark energy.
Okay, thank you.
I also have a quick question to Victor. So in one of your last slides, there is a mysterious phrase about no classical saddle. So can you comment on that, what it means?
Yeah, so, I mean, there's fluctuations in some sense, this long wavelength fluctuations, as of course Alexei first taught us a long time ago, I think just appeared on Zoom. They are classical. And so you could say, okay, maybe there is just some, classical saddle point that I need to find, and that will describe, say, these correlation functions. Okay, but that is not the case. There is no single classical solution that dominates the path integral. In case you need to consider, you need to average over many classical solutions. and they all, contribute roughly with the same weight to the path integral. So that
there is no saddle that would describe all endpoint correlation functions, or
yeah, each classical solution, of course, that contributes. Each classical history, if you want, we like to call them histories in our papers. There's some history of evolution of the field. That each one of them is described. It's described eventually by classical equations. So that corresponds to some saddle and a path integral. But you need to sum over many of them with some weight that is basically given by this probability distribution. Okay, that I described. So that means you need to take into account many classical saddles, and that's what makes this a little bit, not a standard semi-classical expansion. That is the picture. I don't know if it's helpful, this claim, or if it's more confusing, but okay, sometimes you could expect, you just need to find some new, maybe non-trivial saddle point, and that will solve the problem. But that's not the case here. You need to then so there is some, because this field of light, there are many kind of very flat directions in your path integral, if you want. So each of them corresponds to classical saddle, but many of them contribute because some long time in the past there were these quantum fluctuations that somehow let
me ask this. Okay, so very nice question. So if you're interested in extracting one particular observable, non-Gaussianity of some sort out of this whole set of correlation functions and probability distributions, can you still say that that you should take, for example, this particular saddle and you can get to results?
Yeah, this is a good question. So what I talked about is some formal correlation functions, where also related to what Enrico recently said, we kind of marginalize, we insert some detectors, and then we measure state of these detectors, but we really integrate of everything that we do not measure, including some very classical things, like some modes that are very classical that maybe in our universe, it's just, it's some given value, some dipole moment of CMB, something super classical. But in my approach, I would still path integrate over it, okay? Because I'm really computing correlation function, I'm averaging of everything, right? So now you may say, okay, maybe that's not what we really do in observations. And really, at some point, yes, at some point, those effects, I think, become true. Whatever if we measure some mode, right, or probably some very classical modes, we shouldn't really be averaging over them. We should kind of condition on them being something fixed.
Introduce an additional projector.
But this again, you can kind of incorporate. Once you understand this, we really talk about some. You can think of the following. How, say you have this light field, and then maybe some parameter. Electron mass in the universe depends on it. Okay, we can write down a model like this, right? So what we will be predicting will be some, some distribution of the masses of electrons. Say this model is very long, so really we observe only one of them. So in the universe that we see, there is electron has given mass, but in principle there is some distribution in the Hilbert space of masses of electrons. You see the model, I couple electron to this electron mass term stupid, but do something like this. So the proof of principle, right? So that's it. Then of course we measure electron mass once, and we know that in our observable part of the universe, the scalar field had that particular value. Then all these distributions that we had for it, they kind of, become useful because they get projected, right? Yeah. So there is no, it's as it is in quantum mechanics, right? But we were really talking about if it's of some smaller scales, if what we observe, the correlation length of this field is smaller than the observable size of the universe, then we'll see some non-trivial statistics within the observed universe, right? And that this correlation function, the classical correlation functions that I was calculating that describe the statistics, right? Same as always in CMB. Okay, I think I need to run unless there's some other urgent questions for me.
Just a quick comment. Can I ask the speakers to send the slides so that we put them?
I will do one thing.
Okay, yeah, thanks.
Maybe Victor, yeah, before you go, just quick question. So what's your take on this statement by Polyakov and Popov that like the three-dimensional de Sitter doesn't make sense?
Look, I think, okay, I don't know, I can say
Shall I stop?
Yeah, we have to stop this. Yeah.
We have to stop this. Okay, I'll tell you in private.
Okay, sounds good.
So
I think they make a mistake, a technical mistake, okay, in computing a one-loop diagram. But okay, that's what I think. We'll write some paper, short and Lorenz explaining.
Okay, we really have to stop that discussion. Very interesting discussion. So, very interesting day hearing talks about inflation, as I said, controlled by experience and wisdom and a hefty load of enthusiasm. But now we have to change the gears and go for the youth and promise. And in that series, we already have Alexei here starting as the next speaker. He's going to talk us about generational peaks in inflation perturbation spectra due to variable number of slow roll inflatons. So, Alexei, please go ahead anytime you want.
Okay. Do you see my presentation?
Yes, very well.
Okay. Let me see if I can make it full screen. Not quite clear. Okay. Okay. My talk, the topic of my talk will be more phenomenological, so I shall not say any word about higher theory. But the point is that now, from the point of view of observation, we are interested in a hypothetical possibility that we may have peaks in the primordial spectrum at small scales, non-cosmological scales. Why? Once more, we don't have any definite data, but the most interesting possibility is that a part of already seen black holes have primordial origin, and so the question is once more we are much more interested in primordial black holes and related to them, because if we have peaks in the primordial scalar spectrum producing primordial black holes in the second order of perturbation, it generates peak in the primordial gravitational waves, which are much higher than the practically flat spectrum of primordial gravitational waves predicted by inflation. And so, but let me first very shortly summarize what we have from the simplest inflationary models. And my definition of simplicity will be not by considering what are the structure of mathematical constructions or physical constructions, but simply, as you will say, arithmetical one. I shall explain them. So my statement is actually the number of free parameters in these models, which have to be taken from observations only at the present state of science. So the simplest statement is looking at the existing data. At present, the simplest inflationary models are one parametric. Though of course, there exists much more models which have more parameters, and it is in these models that we have a definite target prediction for the amount of primordial gravitational waves. But of course, so that's why I shall very shortly remind you about these models with the aim to explain why these models, which have very different nature, in principle, they have the same the same predictions. So I would say that from the application point of view, speaking about inflation via actually the same models. But of course, to go to have to obtain peaks, one has to go beyond the slow roll approximation, and I shall speak at the end about it's not a new case, but really considered in recent paper with my paper with collaborators about when we have a variable number of slow roll inflatons. So very shortly, how I preferred to formulate the inflationary hypothesis from the beginning, avoiding as far as possible to speak about explanations, because I rank predictions much more than explanations. Okay, so it's simply the assumption that some part of the world was including all this presently observable part was as much symmetric as possible, but still not absolutely symmetric. I shall say a few words about it in the next slide. The only case when I mention about some explanation, but it's not very deep explanation. It's not universal. It's explanation of the cosmological error of time, but only because due to the chosen initial condition. Still, the statement is that the state is not a zero measure state, so it's not a unique state. I shall explain it in the next slide, but the statement, so it's an intermediate attractor and has a non-zero measure in the set of all states before inflation. But what I want to emphasize that because the word inflation is used in many, in a very wide sense, and this often results in its critique, I shall speak about more narrow class of inflationary models, which are based on two independent hypotheses. And by independent, I shall explain in a minute. The first hypothesis refers to the background, so it's the hypothesis about the existence of inflation, the very existence of inflation. So some stage, some finite stage in our past life cone with h dot much less than h squared. And the second statement is about origin of inhomogeneities, but they're produced just from this process, not from any other process, gravitational creation of pairs of particles, antiparticles, and a field of fluctuations during inflation, assumed in the first hypothesis, from which states? From the adiabatic vacuum state, no particle state, not even the correct hypothesis, not for all modes, but for some range of modes. Actually, that's why it's not exactly correct to call it bunch Davis state. So it's not unique. It's not. It's only covering some range of scales up to Hubble and actually much beyond. And what we most interested. As I said, that's just because we need predictions. So what we need actually predictions what have after inflation in the super Hubble region. We need about predictions about primordial spectrum of perturbations. And according to this hypothesis, where the universe was approximately isotropic from sufficiently early time in the past, and then after that time, it appears that though there can exist much more modes, there exist so-called constant modes. Constant mode, actually, in the I should say that in the area of in the inflationary science, there are many misleading terms which should not be all experts, of course, understood all well, but they should not understand too literally. So in particular, I shall, in my talk, I shall net with two cases, the so-called I shall not speak about conservation of perturbations. I shall simply speak about constant modes. Okay, and second, I shall not use the term ultra slow troll, because in fact, what is called sometimes called ultra slow troll is in fact a fast roll. So once more, this is what ultra slow should not be understood in a normal sense. But okay, the statement is, and I shall make it more general in the next slide. There always exist constant modes, approximately constant, in this regime, up to small quantities second order, and this modes has very remarkable property that in this regime they depend only on coordinates. Once more, the simplest picture appears in the synchronous gauge. We have some additional conditions to fix it completely. And when this 3 times 3 matrix, it has a trace path, and then it's easy to check that this trace path is just what is called locally gauge invariant curvature perturbation, but also there exists generically there exists traceless transverse, and this is the normalization conditions. And you see here I use three-dimensional Euclidean metrics, so I include isotropic spatial curvature is also included as a monopole component, and so we can expand it into Fourier series. And what we are actually what is required for any inflationary model is some prediction about this power spectrum. It's logarithmic derivative, which for purely historical reasons it is denoted not simply by ns but ns minus 1. Okay, it's simply a notation, and over erasure of the squares of perturbations. Okay, and so let us make a general remark about the existence of constant quasi-isotropic modes. So there exist other solutions, but in almost all cases they are decaying, and in case where is growing, usually it leads to it does not lead to viable models. And actually for Friedman-Robertson Walker models with vital fluids, this was known already to editions. For a wide class of modified scalar tensor gravity modes, it was probably in this paper. But my remark is actually one even need to specify some new theory to over gravity to check that this will also takes place for this, because it follows simply if for any theory which contains isotropic, especially Fallett, Friedman, Robertson, Walker space-time, which is not degenerate in the mathematical sense of this word. That is that there exist generic illusions which can be arbitrarily close to this solution, and this solution contains 3 gauge constants, simply which correspond to arbitrary prescaling with respect to each coordinate x, y, z, and then simply making this coordinates spatially dependent. It just transforms them into this real physical modes, and then it's straightforward to check that even at this constant, even it need not be small, that they can be arbitrarily large. So the spatial path of the metric in the synchronous gauge is simply a square factor multiplied by this arbitrary 3 times 3 metric. Okay, so that's what we see from delta t over t, and what when we expanded into multiples. Okay, and the red line is just the prediction of this one parametric models. I shall list them. And apart from some features, apart from that feature here, about which I shall say a few words also, and well, a quadruple, which for my opinion is still inside cosmic variance. Okay, whereas you say excellent agreement, okay, and the same we have for E mode, and the third slide, which of the same type, also good agreement, is the causal relation between E mode and delta T over T, and non-trivial predictions of all. Okay, I forgot to say that all non-trivial predictions of all slow roll inflationary models is that this quantity, like models in this quantities are small, and so transformed into polarization. I would say it's non-trivial prediction that B mode should be much less than E mode. It is confirmed. We really see E mode and don't see primordial B mode. Okay, but once more translated from these pictures to the numbers, I would say that from all this can be compressed, all these pictures can be compressed into a statement about the appearance of two new dimensional constants, which the present state of the art we think to be fundamental. It's this first constant, which is small, and this it justifies that using the expansion with respect to this quantity, which is expansion in the power of perturbations, and this quantity, independent quantity, which is also small, and expansion on this quantity completely different one is expansion in the slow parameter, and then the present state of the art in all models, not specifically inflationary one, but non-inflationary to this constant is taken only from observations. In the simplest one, parametric models is possible to predict this quantity, and it was actually predicted more than about 20 years before it was actually measured. And when speaking about some constant is predicted in terms of this quantity, the statement that finally it is the main part up to 10% accuracy, it's related to this quantity, which simply shows how large is the present universe, because what enters here is the cosmic in bit temperature and the Hubble constant. Okay, and so the type of this prediction is simply that this one multiplied by modulus of this one is 2. And you can see it by your own eyes. Okay, so as I said, we don't see B mode, we don't see R, and we have no upper limit on R, and this is the most recent upper limits on R. In particular, it's excludes discussion of inflationary models, and this is a good argument against those who are saying that inflation is not falsifiable. Any concrete inflationary models is falsifiable, as well as any concrete models of elementary particle physics. Okay. So the simplest models, as I said, I use only arithmetical classification. So I'm not saying that models with larger number of terms are worse. They're simply less predictive, so it's more difficult to falsify them. So the most simply falsifiable are one parametric models, and at present we have three types of models which formally has the same prediction in terms of this number n. As I shall show you, the n itself can be slightly different due to post-inflationary evolution. So R plus R squared models, the Higgs inflationary models, and the combined one. So okay, this is my original R plus R squared model. So it has only one parameter, this one, and this is its characteristic prediction. And the same prediction follows from the scalar field models with asymptotically Higgs-like potential and strong non-minimal coupling. The first considered by Spokojny, and when it acquired much more interest when and Shapashnikov identified this scalar field with strong non-minimal coupling with the Higgs field. But why this? Well, you may say that the nature of inflaton in this model is very different. Why they have the same prediction? So once more, from the observational point of view, it's the same model as far as we're speaking about inflationary stage. And the statement is, so though this model one can be considered as a specific kind of fourth order gravity, but once more, a very specific kind, because what was not expected earlier, that this coefficient, if you want to fit observations, should be as large as this one. And the origin of this large coefficient, it is up to coefficients which of the order of the unity, it is just inverse this power spectrum. So just inverse this constant, it is just transfers to this large numbers. Okay, and when one can check that just because this constant is large, quantum loop quantum gravitational interactions are small. Okay, but once more, what I want to emphasize here, why these two models are actually the same model from the phenomenological point of view, from the inflation, because due to the strong coupling, it appears that for large psi, you can actually, during inflation, you may actually even neglect the storm, even if the action, which is usually not possible, but it appears possible in this case, and when R becomes algebraically phi becomes algebraically related to phi, and when once more it appears when you make the following step, which is usually prohibited, to insert solution into the action, and when it appears that this action just transfers to the R plus R squared action for this potential, but with this new m squared. And so once more, and for the same reason, in the more complicated case, because we actually considered also we have both R plus R squared models and okay, the Higgs model or strongly minimally coupled scalar model. It appears that formally this models is two-field inflation. It's actually attracted during inflation. It is also one field, and so once more it reduces to the R plus R squared model with the renormalized m squared. It just given by this condition. The only difference between these models appears after inflation, and it depends to additional assumptions. Not about the inflation, but what is the coupling between either the scalar one in the R plus R squared model or the Higgs in the Higgs inflation, and that's why this capital N in this model is slightly different. If you assume that in case of R plus square, the main effect is to decay into minimally coupled scalar, then you indeed appear some different. But would you assume that the decay occurs into non-minimally coupled scalar with the same characteristic psi which we have in scalar field inflation, then that will be the same. So okay, so conclusion, what we have on the simplest inflationary models, we have a definite prediction about primordial gravitational waves, which are sufficiently small. Actually, this condition is for most models for which slope of the gravitational wave spectrum is not larger than the slope of a scalar spectrum. It is indeed confirmed, and the reasonable assumptions one may expect this condition. And I think Andrei Linde in his next talk will just speak about these models. But once more, here are R, we have no definite prediction on R or the order of estimate. But in the simplest one, parametric models, we have a target predictions, and so this is what was actually used in planning of all experiments. Once more, because as I said, capital N corresponds to the given scale at the present time is slightly different. In these models, more precise measurements of NS1 and NS1 give us information of what happens after inflation. Actually, what is the type of inflaton or scalar couplings to known elementary particles. But once more, that these two are certainly expected discoveries. But two others may exist or maybe they're absent, but we have to be prepared for them at least. Okay, and so first is local non-smooth that features in the scalar power spectrum at cosmological scales first, and then local as enhancement of power spectrum at small, by small I mean non-cosmological scales, which leads to significant amounts of primordial black holes and related peak in the primordial gravitational wave background. Let me remind, I would say the first case, first exact solution, which it leads to the production of large peaks. So the simplest way is to have some feature in the inflaton potential. So the possible origin of this feature in inflaton potential is its coupling to some other fields. So some other fields which, for example, experience the fast phase transition in the course of inflation. But if you, the simplest case, how to obtain a step to obtain is have two features of this that fast break of the first day derivative in the inflaton potential, and when it if this you will see it has one A plus is the derivative of the potential for larger phi, and this is for smaller phi, and then it's possible to obtain this exact solution. And it was, in fact, it was used in this picture. It is this one, but it may be make more. In this simplified version, the potential was assumed even flat-like. But if you now take it into account that it also has some of the derivatives, when one can obtain different type, and a number of solutions of this type actually was used. Shortly mentioned here was used in recent paper, in this last year paper, of maybe you see a large number of well-known collaborators, and the idea is just to try to explain this feature. This feature, okay, this feature, and this feature in the anisotropy. And okay, so I don't have enough time, so let me only present the final results. The final results, I will say that as far as we are looking only on temperature anisotropy, it's possible to find something which fits a little bit better than this minimal one parameter models. But if you add equalization data, it appears that we don't see such features, the corresponding features in the E mode. And so unfortunately, unfortunately, our final conclusion at the present time, it shows that the baseline slow roll inflaton potentials are more preferred than potential features. So okay. So now let's go about possibility to have still we have now let's speak about peaks not at cosmological scales but at scales much much smaller. And then really let me remind you that one possibility, and so actually that's used in different forms, is to consider immutable slow roll inflation. And I would just attract your attention to the fact that in the multiple slow roll inflation, the number of slow roll inflation generically is not constant. During inflation, some fields may go as far as this curvature is not constant, but slowly decreasing. So h naught is not exactly zero. Then, due to the mass terms, some fields may go out of inflation. And that's what, let me remind you this formula, obtained first actually in my old paper. And what is important here is what enters into the sum is not all fields, but only slow roll inflatons. And actually, it follows from the delta n formalism. So the R is actually is a generic formula that is for any slow roll inflation, but it is the creation of the total number of e-folds in the given point, in the given spatial point during inflation with respects to all that well fields. Once more, what enters into both these expressions and in the coordinate presentation and in the Fourier spaces only those that fields are in the slow roll regime. Okay, and it was generalized over arbitrary that we in this paper. Okay, and when it appears that these models those can be used indeed to produce large peaks, and one which I have already mentioned is we have a local feature in the influence potential, the rapid change of the slope, and then an inflection point. But I want to emphasize the arithmetic factor. It's not enough to say an inflection point simply. To obtain large peak, it's a kind of arithmetic statement which I shall repeat also further. To obtain large peak and increase in the power spectrum of the order of 10 to the power 8 times, that is what we need to obtain a significant number of primordial black holes. The initial model should contain some large part parameter too. So in particular, in the case of inflection point, it should be if for example, this parameter is still not large, when one should have a large the derivative of a potential. When the rapid turn of the inflaton trajectory, when transitions leading to the large as a perturbation. But once more, a novel, but actually once more, it's not a novel way. It was already in my original paper, but if you don't assume large coefficients, then the resulting peaks will be not large. And so that's why in this paper, and this is actually I'm close to my end, if we consider two field in this recent paper, we considered two-field inflation with the different inflaton effective masses, which leads to stages of inflation and large non-standard kinetic couplets. Large means, and here is the way in which these large coefficients appear. So the upsetting is that the model produces large peaks if it contains large beats. Another thing that the relation is approximately exponential. So to obtain increase to the 10 in power 8 times, you need the p of the order, say, between 10 and slightly more than 10, but still it is large. Okay, and when it says it can be shown whether it's research to the formation of primordial black holes and to generation of stochastic background, and this is the effect appears just at this case when the first inflation, the first stage of inflation ends, and when it appears we have a very jump. Unfortunately, we still cannot update analytic expression, so it's only a result in numerical calculation. Epsilon is still less than unity part per second, but the eta parameter is very large, and so depending on the parameter, it can produce large peaks in the primordial scalar spectrum. In the linear gravitational waves, we don't have any features, but if you consider second order effects using Weber's standard string, then it's possible to have also large peaks in the gravitational wave background. Okay, and then so my conclusions. So of course this model has two additional parameters which have to be taken only from observation, and the first parameter is the location of this peak, and the second parameter, depending on B, it's the height of this peak. So once these models have at least two additional parameters. So my conclusion is that simplest inflationary models without features, they are one parametric. Of course, once more, there can exist much more complicated models, but they have less predictive power. But and the three models which have the same target predictions for R, but the actual values of n, which enters here, are slightly different, but not due to inflation, but due to post-inflationary reheating. In the two-field model, it's possible to produce a large peak at small scales, depending on the assumed parameter. So once more, large peaks in the spectrum require a large value of sum, at least one of a model parameter. But returning now at cosmological scales, our analysis at present state shows that the present temperature, and then you consider not only anisotropy, but polarization too, they do not favor models with features, although they are not able to exclude them completely. Thank you. Okay, I can stop sharing. Okay, raise hands. Okay, Anna has a question.
Sure. Anna, go ahead.
Hello. Thank you for the very nice talk. My question concerns the model with two scalar fields. Actually, what is the cutoff scale in this model? In the case if you need some large parameter there, couldn't it happen that the cutoff scale is too low in this case?
Well, actually, I showed in the slide, I showed that by using different values, so that values were the value of phi zero in these models and B, it's possible to have this peak at any scale, and correspondingly the primordial black holes with any mass. So all restrictions that follows, I showed you very shortly the observational restriction, well-known observational restriction of primordial black holes with statement that with this, as I said, this models has two additional parameters, and with these parameters we are prepared, I would say, to explain any scale and any amount of primordial black hole. So the answer should follow from observations only.
Okay, thank you. But I was asking actually about theoretical consistency of the model. I mean, by cutoff scale, I mean the scale of strong coupling, which can happen due to the presence of exponent in with the kinetic term.
Well, as I said, it's the exponent B phi. Then okay, I already so you can find it on paper. So once more, it's typical. Actually, it's m squared phi squared models phi itself, but it's coupling. It's coupling to another field. It's exponent b kappa phi. So it's actually due to this coupling. It's some Planckian. The effect that occurs when the field is sub-Planckian. So it's m Planck divided by this large coupling B. So in this sense, so it is no worse as any even field model.
Okay, thank you.
Do you have any other questions or comments? Is this one hand? Oh, there was no. Is that one hand that I see? Anna's hand, I suppose. Yeah.
Sebastian, hand.
Okay, so yeah. Go ahead, please.
Yeah, thanks a lot for the talk. So just to make sure I understood correctly, so as you said, one can produce in a single field model, one can produce primordial black holes by an inflection point. But somehow you argued against that. Was that that this is that there's something bad about that? I don't know if I understood correctly.
No, I am not against this model. I'm saying that about thing that which is usually not explicitly stated by people. Some write some potential in a figure. My statement is that if about some hidden information in all this paper, so the large peaks in this models appears if in the inflection, it's not simply an inflection point in which the second derivative is zero. The statement is that additionally it should have some specific feature that the third derivative should be large. So in this is usually not emphasized.
Okay, yeah, thank you.
Okay, maybe one quick question from Juan Carlos, if you want.
Yep, thank you. Just quickly, a lot of the black holes that may be formed from peaks at the spectrum at small scales are too tiny, and they might quickly evaporate. So how confident are you in using relics left behind after the evaporation to constrain the abundance of these black holes?
Okay, in the papers I mentioned before, just for this reason, because just I would say these small black holes at less than 10 our 15 grams are almost excluded. So that's why we consider we don't consider parameter for which such black holes are formed. Once more, so I repeat. So depending on these parameters, you may obtain any black hole's mass. But when you simply compare your prediction with well-known upper limits on the primordial black holes, and then much more, it's not from our model, it's from observation. It follows, for example, if you want to have primordial dark black holes, which now comprise all non-relativistic dark matter, then it's possible, okay, for black hole masses between 10 to 17 to 10 to 22 grams, I think. But in case of solar black holes, they cannot have comprise the all non-periodic dark matter, but still, okay, there is still, I would say, conservative estimate. They still may comprise, say, about 10% of it. So it's not excluded that part of the black holes which we see on non-gravitational wave antennas, that not all of them, I would say cautiously, but some of them I still have a primordial origin.
Okay, thanks.
Okay, so thank you again, Alexei, for this talk. Nice talk, and but we have to move on. So our last speaker today then is Professor Linde, and he's going to talk about cosmological attractors after the recent data, I suppose, Planck, BICEP, and Keck. Go ahead. Are you muted first? At least I don't hear anything.
Yes.
Okay.
Now I hear. Yes.
Okay, good. So first of all, thanks for inviting me here, and I am very happy to see here virtually many of my friends. And let me talk about these cosmological attractors before going to the main content of my talk, which will be about cosmological attractors. I may add something maybe to the reply of Alexei about the origin of exponents in his model. Recently, in our paper with Renata Kalash, we were able to implement models of his type in the context of cosmological attractors in supergravity. So if you want to know more about that, there are some a paper about that, but I'm not going to discuss it in my talk. Now, about the cosmological attractors, the main goal of the talk is the following. First of all, part of the talk, maybe some of you already have seen, the last part contains some news. So first, it is discussing inflation and its status after Planck 18, and also after recent BICEP Keck results. The second thing is to identify simple models where a single parameter is sufficient to describe all presently available data. Because if I do not care about this single parameter, I can describe all data by Planck 2018 and BICEP by simple models of polynomial with third degree, and that's it. But if you want to do something simple, elegant, like Starobinsky model, for example, we need to work a little bit. The third goal is to find future-safe models which have a possibility to describe future data if, for example, we will find tensor modes with a magnitude much greater than 10 to the minus 3 or much smaller than 10 to the minus 3. So how can we describe it? And also what will happen if we decide that we need to unify CMB data from BICEP and Planck together with supernova. Maybe we need to change something. So these models, first of all, describe some predictions, and second, they exhibit certain flexibility, which I will describe in the end of the talk. Okay, so now let's go. Why is that? Oh, that's the thing. Okay, I'm in the wrong mode. So here is what I've shown you. And now about this Planck and BICEP Keck. The new results, I'm sure that most of you have seen them, is the following. This is blue ellipse downstairs, which shows you the data preferable by all of this set of experiments. And this suggests that no simple models, monomial models, phi squared, phi to the 2/3, whatever, match the data, which is a strong constraint. Another, here is the simplest model of natural inflation, also are out. It's always possible to twist something and to change something, but the simplest models are out. And then the question is, what remains? And then another thing, looking at what we have here, is prospects of what we are going to look for in the future. And so in this picture, we see here again this summary of Planck and BICEP data. And here are some projections of what can be done by LightBird. And here we see some possible targets. So one of them is Higgs model. Oops. Okay. One of them is Higgs. Okay. One of them is Higgs model, which is shown here by a dot. Another is a red line. I'm a bit skeptical about the place where they put this red line, but this is supposed to describe Starobinsky model. I would think that it's slightly to the right, but it depends on who draws the the projections, I think. And these violet or purple lines correspond to some predictions of alpha attractors, which I'm going to describe in their particular realization in extended supergravity, which were developed by Ferrara and Renato College. So I'll mention it later. But what we see that in all of these projections, the right part of this NS and R is not filled. So only left part of what BICEP and Planck prefer, only this left part is covered by the simplest models. So what will happen if actually we find something to the left? Do we have any reasonable model or not? And that will be also a subject of a discussion. But first, I indeed mentioned that if we just want to fit something, it's possible to fit the data by a model with many parameters. But if you want to just be lucky and get something simple, then lucky comes difficult. This is from the page from the paper on inflation by Planck 2018, where they listed all models available at that time which they wanted to explore. It's not all existing models. These are the simplest models in the sense which I mentioned to you. Minimal amount of parameters, and let's see what happens. So it is a Starobinsky model here. It's there is a Higgs inflation with non-minimal coupling like that, and there are lots in between. And what happened later, that these models survived, and this model was ruled out and decisively right now by BICEP. And this model was ruled out again, the simplest one only. This one was ruled out. I will tell you more about this, and this one too. And that's what remains. So what remains is, for example, again, Starobinsky and Higgs models, they're here. And also the set of alpha attractors, which are capable of describing the same values of NS as these two famous models. But also, in addition, they have flexibility in describing different values of R. And I should mention that eventually there was already a set of different models which possess similar flexibility. One of them was recently proposed by Starobinsky and his co-author, and there are many others. So I will describe only the models which were originally proposed because I just know them better. But it should be understood that we are not alone in this interesting place. Now, there are two types of these models which I will distinguish from. One of them we called Tanch squared model, we call it T model, this kind of potential. And another is, we called it E model. For alpha equal 1, it is just a Starobinsky model, but we have right now freedom of the choice of parameter and the idea behind them. I will explain you what the idea. But before going there, I should mention something about this green area, which was supposed to be populated by hilltop inflation. And I have mentioned it already at some other conferences, so maybe some of you have seen that if you consider the simplest model like that, constant minus phi to the force divided m to the force, which is drawn here, then the results which are shown here apply only to the models where the parameter m here is super Planckian, like 10 times greater. And when m becomes smaller, then you go way to the left, and this smaller part is already ruled out. But if m is actually very large, then this is what we see. And it is very difficult to adjust the shape of the model near the place where this potential inevitably kicks 0 when phi becomes equal to m to the force. And at the place where it goes through 0, it's actually linear and goes like a stone through this cosmological constant equal to 0. Field phi after that continue evolving down, and the universe immediately collapses. So these models, literally, they have been ruled out. They just, well, computer models calculating NS, they do not care about subtlety like global collapse of the universe. They stop at the moment when slow roll stops. So they produce nice looking pictures, but these pictures are misleading and the models are ruled out. It's possible to modify them somehow. And one simple modification was, of course, the Coleman-Weinberg model, which is kind of hilltop with the logarithmic corrections to phi to the force. But right now, this is shown by these two orange lines here, and the BICEP data ruled out even this model. And I should mention also, even this part is kind of okay-ish, but only when spontaneous symmetry breaking is super Planckian, which was not something which was originally planned. Okay, so gone with this, and this is what remains. We have alpha attractors. Here is the idea of this kind of models. We may start with the simplest quadratic theory, m squared phi squared, and change only one thing. Change here kinetic term. This is just one option to introduce this model. Change kinetic term at here phi squared divided by 6 alpha in the denominator. And you may ask me how we got this idea, and I will tell you if you ask me. But right now, let's just look at what we have here. It looks like a singularity. It looks like a dangerous story. But if you change your variable to a canonical one, then the singularity goes to infinity, and what you have just a switch of variables, phi equal to tanh of phi divided by this. Potential becomes tanh, and this is the origin of tanh models. And these models were discussed in lots of details, and their predictions they produce the same value of NS as Starobinsky and Higgs inflation, but they are producing flexible value of R. Now, more generally, one can consider any models of that type with any potential V of phi, which grows at large phi. And then after going to canonical variables, it becomes V of tanh of phi. And at large values of the inflaton field, only this asymptotic term is important. So independently of what was the original shape of the potential, you more or less always have, well, in most cases, this kind of model, and that is the reason of the universality of the answer. So non-sensitivity of this model to the shape of potential is very interesting. Now, more generally, yeah, that's what I've just shown, and the answer of the predictions are ns equal to 1 minus 2 divided by number of e-foldings, and r is 12 alpha divided by n squared. For Starobinsky model, it would be alpha equal 1. And the meaning of what of the trick which we just made is illustrated like that. You can take any wiggly potential generated by your computer reading sinusoidal waves. That's how I did it. And then you stretch it, you go to canonical variables, and what you have, well, this exponentially flat potential, and then the field rolls down to the minimum, which lead to these universal predictions of this type. And if you want to generate two-dimensional landscape, you generate two-dimensional landscape. For example, one of these fields is normal canonical and another is of alpha attractor type. And after go to canonical variables, you have here again plateaus, which make the potential flat, and then the same results. Or you can do differently. You can start with a model d rho over rho squared, and then you go to canonical variables, and then you obtain these E models of this type. So almost same predictions, asymptotically they look the same. So you have this large class of models, and that's how their potential look for T inflation, T model to the left, E model to the right. So the main message here is that alpha attractor mechanism makes the potential flat, which makes inflation possible, because usually if you just generate random landscape, you not always get inflation. And in the context of alpha attractors, you get inflation most of the time if you wish. And then this also, once inflation starts, it makes the universe flat. So this is kind of nice conspiracy. And how it looks at the plot of Planck and BICEP, that's how you see these yellow lines show the prediction of simplest T models, and the red lines show the prediction of E models generalizing Starobinsky. And as you see, all of them are close, partially cut through this preferable area. If I modify slightly the models, consider not simplest, but next to the simplest, I start with a theory phi cube, phi squared, phi whatever. All of these models which are ruled right now, ruled out by BICEP, and I made this generation in terms of alpha attractors. You see that all of these models, their prediction moved down to the area where they all match experimental data. So this is pretty convenient mechanism of reducing multitude of different models to essentially the same prediction in the limit of small values of alpha, small values of R. That's a picture from, let me move something here. Okay, no, I can't. So this is from the talk by Flogger at CMBS4. So this is what happened with BICEP and Planck, and here is Starobinsky model and Higgs inflation. This line corresponds also to another interesting model, which is fiber inflation. It's related to string theory, and these are the lines which correspond to these discrete predictions for alpha attractors, because in general parameter alpha can take any value from 0 to very large one. But if you are in the context of some models motivated by maximal supersymmetry, supergravity, or string theory, then there are some preferable targets which starts at the lower one, corresponding to alpha equal to 1/3, and going higher corresponding to alpha equal to 7/3. And this alpha 7/3 is at the level r about 10 to the minus 2, which makes it a very interesting target for observations right now. Okay. Now, where is this target corresponding to the upper line? So it just, my mouse does not obey me. Okay, so if you look at this yellow line, this is alpha equal to 7/3 for T models, and red line is a line corresponding to alpha 7/3 for E models. And as you, my God, what is going on? Okay, and this line crosses exactly the center of the results by BICEP and Keck. And it is even tempting to say, oh my God, maybe they just confirmed this model. But of course, it's very, very too early, much too early to make any judgment, because the error bars are comparable to the signal. So we will need to wait for a long time until we come to any conclusions about that. But we have lots of other ladders in this graph to verify. But that's quite interesting that their projection is that within 5 years, maybe with good luck, they will be able to measure just on the BICEP. Okay, so it's not satellites or something. Okay, maybe they will measure a sigma r with the accuracy about the 3000s, which is, if it is great, if it happens, it's going to be great. Okay, after the paper, there was another paper claiming that the increasing and strengthening the constraint which obtained by BICEP and Planck, using the same BICEP data and using the same Planck data as before. But they said that they use Planck data in a different way, emphasizing some different stuff. And what is interesting here, that they more or less draw very similar ellipse here, but this ellipse slightly shifted to the left. And when we ask them what's about this ellipse shifting to the left, they say that, yeah, but we are considering this Planck data differently. Then I asked about the same effect. I asked other people from Planck, like Evstasio, and Evstasio said, don't trust them because they, methodologically did something wrong. And so I don't know. I'm just listening, showing here 2 different sets of papers. They give approximately the same results, but with some variations, and we will see how it all going to play later. Returning to all of these projections to the future, the question which we are going to study, whether there are any reasonable models which would explain, predict something to the left or to the right of this blue area, because if not, then do we really going to put all our eggs in the same basket, like we are just making a bet that this is right, because it is expensive to go here. If we don't have any targets, then does it really reverse the game? And so I will just give some examples. This is yet another attractor model, which is a generalization of Higgs inflation. We played with it also about 10 years ago. So we in the Higgs inflation, we have here xi multiplied by phi squared, and here it will be phi to the 4th to the right hand side. But if we just write here xi multiplied by arbitrary function f of phi and put here square of this function, it also works, and it gives the same predictions. And attractor regime, however, is reached in an interesting way. If you start, for example, with these models which we have shown, like phi to the 4th, phi to the 3rd, phi squared, phi whatever. When the xi goes to infinity, the predictions, again zoom to this area. But what's interesting is that they spend quite a lot of time in the broader area here. This is a logarithmic scale for the same predictions. So they all zoom here, and they have this feature that all of them leads to predictions of R about 10 to the minus 3. So it's not covering, not goes all the way down like alpha attractors, but that's what they do. And they span a very broad area of different values of NS. So we have some models to cover these other values of NS as well. Oops. But then we consider it more general model. And this more general model contained general function omega here, general function k here in front of d phi squared. And if we consider specific choice of these functions written here, then it's possible to show that this is exactly alpha attractor. Okay, and so what I'm trying to say that it is possible to obtain in this class of non-minimal modifications of gravity, you can reproduce all predictions of alpha attractors. In particular, R can take any value going to 0. This is a general pole inflation, which is a generalization of simplest alpha attractors. So you can study in alpha attractors here, the rho is to the second degree, but we can consider any pole like that. And for q equal 2, we have alpha attractors. For q greater than 2 and small r, we also have an attractor regime, which with the, with these predictions, ns equal to 1 minus beta divided by ne, where beta is related the following way to q minus 1, and q is the power here. And you can reproduce many interesting plateau inflation models in this class of general pole inflation. So previously we considered only models which approach plateau exponentially, but if you consider this more general pole inflation, then you can reproduce potentials which approach plateau polynomially. And these are predictions for different models. So we can have models which cover by their predictions essentially the whole area to the right of well, alpha attractors, all area which is presently favored by Planck can be covered by this class of models. And the question is, but can we fit it also into alpha attractors? And the reason to look for it is because alpha attractors are conveniently fit into many models of supergravity. So it is, it would be tempting to try to implement it in the more familiar context, but usually we have this excuse me, exponential limit at infinity because we well imposed the constraints on V, that we just represent V of this singular parameter rho through Taylor expansion starting from rho to the 0 and to the first degree, because we assume that potential and its derivatives are not to be singular for simplicity. But if you allow potential to be non-singular, but its derivatives can be singular, which is okay, your potential looks look normal, then you can start with original rho potential in terms of rho variables having logarithmic singularity. Potential does not have singularity, but its derivative will have. And then if we switch to canonical variable, we have all of these plateau potentials, which I just mentioned. And by doing this, we can cover all values of NS from 1 minus 2 divided by NE to 1 minus 1 divided by NE. All of them can be covered by this set of models, which we call polynomial alpha attractors. And so if we are thinking about the future of light bird, we know that it's possible to cover the right-hand side of it by either pole inflation or by these polynomial alpha attractors. And a nice feature of all of these models is that at small values of R, all of these predictions, they just go down vertically, which means that we can, if we measure NS, which becomes a very part of the game, then we know to which class of the models this model belongs. And after that, we will know the second parameter of this model, which determines the value of R. Right now, you can take this parameter in a broad range, but later, if we find gravitational waves, then we will be able to determine, well, to certain accuracy, whether this model belongs to one class or another class of these attractors, and what are the parameters responsible for the values of R. So that's how it looks if it is compared to the CMB-S4 recent white paper. That is the projection of what S4 may achieve, and that is Higgs, that is Starobinsky. This is a ladder of predictions due to Ferrari and Renata Kalisz, and all of these models which I mentioned are shown here. And then the question was, can we do even more? And of course, who needs more if you have everything that we need at the moment? However, if you watch what is going on with this H0 problem, then there are some people who are well using this N0 problem to argue that we must reconsider everything, adding well, exotic models of dark energy, for example. Sometimes you use their models and take the same data by Planck and by everything else, try to produce something which would match all of these experiments together in a consistent way, which is not an easy game, okay? And then in some of these models, the same Planck data in combination with everything suggests that maybe NS is even equal to 1, okay? So I do not know how seriously should we take it, but let's just prepare if it does not cost us much, okay? So what we decided to do and to check whether there are any attractors which would predict NS equal 1. And surprisingly, yes, there are some models which are attractors in this respect. And there are hybrid inflation models which exist a long time ago. So hybrid inflation, the simplest model of that, it has, this is m squared, phi squared. This is like Higgs model for a different field, and that's the interaction here, okay? So at large value of field phi, the potential shows this narrow valley, and the field rolls down here, and it's only field phi that evolves. So everything is calculated as in a normal inflationary model, except for this term uplifts the potential. So the potential is higher than m squared phi squared. And this allows lots of different possibilities. And then eventually, when it goes to this place, potential is destabilized and you roll down to one of the two minimum. Okay, so the property of NS here, NS is 1 minus these derivatives and the derivatives. If you take this uplift very, very large, uplift does not change V prime, and uplift does not change V2 primes for the same value of phi, but it increases V. And as a result, NS becomes equal asymptotically with very large uplift. NS tends to become exactly equal 1. So we have interesting attractor behavior here. So we decided to check what happens if we generalize these models and make them alpha attractors in both of these fields, alpha attractors. Not necessarily in both. One is already interesting, but let's do it in both. And the same potential as it was in the 90s in well, my original models. So just as in alpha attractors, interestingly, when you study the evolution, you solve these equations and you find out that just as in alpha attractors, you have a universal large N attractor prediction, the same as in normal alpha attractors. So universality is here. However, if uplift is very large, then this large N, which is necessary for universality, is achieved only for N much greater than 60. I emphasize, if uplift is very large, okay? So if we increase uplift, then we gradually shift towards the original hybrid inflation large uplift prediction NS equal 1. So what we have right now, you write down models which look like, and this was discussed in this set of models, which look like alpha attractors. And we studied similar models in supergravity, in string theory motivated models, etc. And quite often we see that there are more than one field evolves. So we always assumed, and sometimes checked, but always assumed that the predictions of these models are given by standard alpha attractor predictions. However, what we have learned that this uplift may change predictions of the alpha attractor model if it is sufficiently large. Okay, so that gives us some flexibility. Whether this flexibility is desirable or not, we don't know, but we should understand that after uplifting this model to the left may lead to different predictions. Now, this model also has another interesting feature. See, usually this model here have one valley, but if this valley achieved at the moment when well, interaction between scalar field phi and sigma becomes well, strong enough, weak enough, and you have instability realized here. But if we use alpha attractors, then this position of this point for some parameters alpha becomes at infinity, okay? And therefore always you have two valleys. After you make this transition to alpha attractors, for certain choice of parameters, you always have two valleys, and your trajectory goes this way, okay? So first of all, you never get any topological defects in these models. And in some alpha attractors model, this is a real problem, okay? So that's a new class of models. Actually, it's not entirely new. There were some hybrid inflation models of this type, which do not have topological defects, but this comes here naturally in this context of alpha attractors. And then if you play with another parameter, beta here, which describes this part of the potential and the lowest part, then you will see that actually this potential does not have any minimum at all, because this minimum have run to infinity. And in this case, you go down and you roll here, and you have quintessential ending of this model, which leads to dark energy asymptotically determined by the parameters of this model. So it's quite interesting that we just have hybrid inflation. We just decided to play this game, and we only started playing it, and we simultaneously see that in this model we may not have topological defects, and we may have quintessence here, and so the models becomes very, very rich. We did not explore all of its possibility, and this is just in the process. So I am concluding my talk by this. So first of all, many predictions of inflation theory have been already tested and confirmed by observations during the last 40 years. Some inflationary models, such as Starobinsky and Higgs and broad class of alpha attractors, can describe all presently available data by a single parameter. You may need the second parameter if you find gravitational waves, then produced by inflation. Then you need to, it will determine the value of a second parameter, which is flexible in alpha attractors. Predictions are very stable with respect to significant modifications of the potential, which is interesting. These models, just like more general versions of pole inflation, they can describe any small values of R, all the way down to R equals 0. I have seen many times that people who are writing these projections for CMBS4 are saying something like that. If we do not find R at the level 10 to the minus 3, this will rule all our models existing at the moment, and we will need to return to drawing board, and who knows what will happen then. So these people apparently do not read the literature over the last 10 years and still make their judgment, okay? And then BICEP and Keck results are moving very close to the range necessary for testing tensor models in these models, especially because we have targets at the level 10 to the minus 2, not only 10 to the minus 3. So some of the models of this type will be tested. And also, if we try hard, we can add considerable flexibility to this class of models. So we can have models, we have double attractor, like in hybrid inflation, and depending which parameter you vary, you have either one of the predictions or another, or if you are well-spoiled person like some of us who want to have complete freedom, we can change both of these parameters and get whatever value of NS that we want. This is not very nice, like how about the predictivity of this? Well, this requires a pretty sophisticated models with lots of parameters like hybrid inflation. So this is not a generic prediction. But in the future, maybe we will be happy that we have this flexibility. Okay, thank you very much, and I finished.
Okay, thank you for this talk. So it's true what we say in Finland, as the evening draws longer, the party just gets better. We have several questions, I believe. So who was first? I didn't check. So maybe we start with the age before beauty. So Valerie, please. You hear me?
Okay. Hello, Andrei. I haven't got it. You're talking about the hilltop potential with minus quartic scalar field. What's wrong with this scenario?
Okay, then I need to run away to my transparency on that, because it explains something in a very cryptic way.
Yeah, that was pretty cryptic indeed.
Yeah. Okay, here we are. So this potential is unbounded from below. Okay, now if you take it literally, it's just a disaster and it ruled out. If you want to modify it, you're welcome to modify it. And this potential was very popular for a good reason a long time ago, when David Lice in particular emphasized that if you take M much smaller than Planckian, then modifications of the shape of the potential downstairs where it hits the ground do not affect inflationary predictions. You just bend something downstairs, nobody cares. Okay. Now, if you consider, however, this region here, the green region, you will see that all data which fit the Planckian data, they all correspond to M about 10 Planckian masses. Okay? So now if you try to bend this, you will find it a very difficult thing, because if you try to bend this, then potential typically will become quadratic. That is natural shape of potential downstairs. And if you have a potential which is linear when it hits the ground, that is why you get these 2 points like an attractor points here. If, however, you bend it and it becomes quadratic, then these points of M squared, phi squared up, these will be the leading points, points to which these predictions go. And that's what we see here in the prediction of Coleman-Weinberg potential. Coleman-Weinberg potential predictions ends here at phi squared. They are twice as high as these predictions here. So you cannot smoothly bend this potential into something reasonable. And if you bend, instead of linear hitting the ground, you have quadratic bouncing from the ground, totally different predictions. So this totally different, it becomes a different model, not this, but this, and even with much higher R, and even this model is almost exactly ruled out. If you want to change it abruptly here, it's possible. For example, you can consider model hitting the ground and consider it as an absolute value of it. That would be ridiculous, but if you just want to play with absolute value of square root of something, so it's possible to do it. But this is not single parameter model like it was nice and beautiful here, which apart for V0, it just gives you the scale of perturbations. But this is single parameter. And for small m, it was beautiful. But for large M, it becomes ugly and nobody notices it because computer programs, they compute this area, and when the field hits the ground and goes to anti-de-Sitter, they stop calculating before that because, well, whatever. So it was just like that.
I had a technical problem. Is that because you? Is that I had a technical problem? I didn't hear some parts of your.
Okay.
And the answer is that because you don't want this scalar field to be super Planckian?
No. What I said, okay, is that this part of the graph, the part of the graph which fits, which is consistent with the Planckian data, this part requires M to be super Planckian. Okay.
Right.
Nothing wrong with this field being super Planckian. But if it is super Planckian, then the potential go down like that, and it hits the ground. And then this model is ruled out unless you form a minimum here. Now, forming a minimum when the scale of change of the potential is 10 Planckian masses, 10, it's not 1, 10 Planckian masses, then you will have quadratic potential on the scale 10 Planckian masses, and your inflation will be effectively quadratic. It will be quadratic chaotic inflation. And that is why I'm not just talking about this, but this shows you the result of the calculation, this for Coleman-Weinberg. So the whole curve shifts upwards.
Okay, thank you.
Okay, so maybe next Scott, and then after that, Laura. So Scott, please go ahead.
Hi, thanks for the talk. Very good. I just have a question about the what I'm assuming is the Kähler potential correction to the kinetic term. Can you comment on corrections to the Kähler potential in the eta problem?
Let's look first at the problem here. Eta problem in the original one was very pronounced. Like if I add here lambda phi to the force, then all of my predictions change. If I have this kind of theory and you add here lambda phi to the force, you have the same predictions. So eta problem in the standard understanding of it, it does not exist here. The question is how good this Kähler potential is, how good is in terms of supergravity. So what I say is that the Kähler potential which we are using here is pretty standard in supergravity. There are two types of them. One of them log of t plus t bar, and another is well, 1 minus zz bar, something like logarithm of that. So these Kähler potentials are often used. If you start thinking what will happen with the radiative corrections to these Kähler potentials, that's a different issue. I'm just saying that this kind of scenario appears in supergravity in a relatively natural way, and you study lots of details about that in some of our papers.
Yeah, very good. Thank you.
Okay. Then Laura, please go ahead.
Yes, thanks. Thanks a lot for the really nice talk. So I have a question that is, where did you get the idea of having a pole here? So to modify in this way the kinetic term. And then the second is about the hybrid alpha attractor model that you presented at the end. So it might be interesting to see if with alpha small enough, you could have some interesting multi-field effects in that sort of model. And I was just asking if you did look into that, or if you think it might be an interesting avenue.
Okay, so first about the first question, it was kind of interesting. In 2013, we were looking which models fit all the data. magically there are two different models, completely different at first glance, Starobinsky model and Higgs inflation. We start studying them, carefully looking what is in their structure, which makes the predictions so similar. So you start, for example, with Higgs inflation, and we move from it to the model where the interaction with gravity is minimal. In between of this motion, at some intermediate stage of calculations, you get these, singular kinetic terms. They appear just at the intermediate stage, so you may ignore it, but we paid attention. Then we looked at Starobinsky model R plus R squared, which was also formulated in terms of exponential potential of a scalar field approaching infinity exponentially slowly. Okay, so on the way from R plus R squared, you make some metric, the change of G mu and the change of scalar field. And in the change of this midst of this transformation, there is one stage, if you look at this carefully, when you also temporarily get this kinetic term, which also looks singular. Okay, so we have coincidence between these two models. Then we studied a different model where you start with completely different principle. We called it conformal, superconformal, attractor, whatever. And we studied with one fake field, one real field, then the fake field disappears. And the process of disappearing, you have in an intermediate stage, the singular kinetic term also give the same predictions as Starobinsky model of Higgs inflation. And then we decided, well, why don't we just look seriously on stuff like that? Okay, so this is how we found that if we just pay attention to these terms, we have a general prediction for a very broad class of models. The way to it was slightly more complicated, but this is just a unifying idea. Okay, so now talking about hybrid inflation. Well, the first part of this discussion is how you change predictions for them. And for that, you need only the simple model like that. The second part, if you just play a little bit with the parameter alpha, then you have already very non-trivial effect, which is a normal scenario you cannot find. And then here, if you have beta sufficiently small, then you have quintessence. So these already show you that the interaction between these two fields, which look pretty simple, it may be just quadratic interaction, but in the context of alpha attractors, it leads to several dynamical regimes which we could not imagine before. And in particular, if you look at the last model here, spontaneous symmetry breaking in this model can easily be super Planckian. And the same in the second model to the right. Spontaneous symmetry breaking can be easily super Planckian. If you have a transition from the barrier to the right, and this transition is super Planckian, you have a second stage of inflation at this place. And then if you start your transition not exactly at the reach, but close to the reach, then you generate large perturbations producing primordial black holes. So this is a mechanism which we discussed already, I don't know, maybe 20 years ago in our paper with Juan Garcia Bellido a long time ago for hybrid inflation. But there it was kind of tricky. And in these kind of models, it's easily appears. So you can use it in the mechanism of black hole production, certainly.
Thanks. Just one last question. So on the plot in the right, are you turning down alpha or up? That is for smaller alpha or for larger alpha?
Yeah, let me figure it out. I believe that this is for small alpha, yes.
Okay, thanks.
You may find the answer in our paper, which we have written. It's already 1 hour into the talk, so I'm already dismayed.
Okay, we have
a small alpha.
And one more question, at least from Misha, please.
Yeah, hi, Andrei. So question, so you described many different models of inflation. And so I have kind of, maybe this is philosophical question. Do you see any way to reduce the freedom?
Maybe, Misha, why do you live in Switzerland? I don't know, with ideas like that. Okay, so the models of alpha attractors, they actually reduce the freedom pretty substantially, because you take arbitrary potential and making one single assumption about this singular kinetic term, you reduce the prediction to just one simple prediction. So the beauty of it was that instead of just fighting what kind of potential do you need, and inflationary models are unpredictable because they predict whatever you want. Okay, the freedom was reduced. On the other hand, I also remember that when people were coming in the US to the shelf and looking for different type of coffee, I have heard anecdotic stories that some of them just break down because they could not make a decision because there were too many types of coffee. So those people who have too many types of coffee may dream about reducing their choice. Okay, I think that it's good if you have many choices, but if the choices are more predictive, of course, it's better. In particular, I'm not very happy that these hybrid inflation have too many predictions. Okay, but that comes to by the price. See how many parameters I needed to add to the story.
Okay, thank you.
Okay, it's already quite late. Do we have still Hauri wants to have a? Hauri, please go ahead.
Yes, thank you very much for the for interesting talk. My question is that do you have any physical interpretation why a singular kinetic term can? I mean, what is the physics behind it? Why should it work?
Okay, the reason why singular term works, or the reason why singular term is natural?
I mean, what is why? Because the modified kinetic term you can in Jordan term can be considered as a modification of gravity. Now, which type of modification and what would be its? I mean, really. Physics behind it, the symmetry or something like that? Huh?
Well, so first of all, I'm not talking here about modifications of gravity, though these type of singular terms, as I said, they appear in the intermediate stage of translation between Starobinsky model R plus R squared to the model with Einstein theory. So these terms do appear in several different contexts, as well as in Higgs inflation. So this, just to answer that, this is not something which was specifically invented to, was it specific? No, we had the third model, as I said. And when we have seen it 3 times in a totally different context.
No, I understand. I understand.
Why does it work?
What's the physics behind it? I mean.
Yes. Okay. Well, mathematics maybe why. Because if you look at this pole and you try to go to the pole, then your denominator becomes smaller and smaller and smaller. Okay. And if you want to go to kinetic terms which are normal, like canonical, then you see, oh, my term in the denominator becomes smaller, which means that I have a huge factor standing in front of d phi. And this huge factor standing in front of d phi is equivalent to stretching effective potential. So this stretching of effective potential is the result of this transformation which we got here. you, instead of, well, this philosophy, you may really just, well, solve these differential equations to go to canonical, and that's exactly what you have. You have potential, which is a function of tangent. It's not a potential function of phi.
Yeah, but this is again a mathematical description. This
yeah,
does
so
not
I
say
tried to
what,
give you intuition.
What is physics? I mean, why nature has done that? Huh? This is my question.
How do I know that nature took this way? It's just if you have Starobinsky model, Higgs inflation, some other model do these, and then we go to supergravity and we find Keller potentials which lead to kinetic terms like that. We say, well, why don't we use the gift which other people give us?
Yeah. Okay. Thank you very much for this answer. Thank you.
Thanks. So, Valerie, do you have is that your old hand or have you been wanting to ask another question?
It's okay.
No, I don't have any other question.
Okay, so then we have. Okay, thanks.
Oh, I'm sorry. I should have lowered my hand.
Okay, so we have one more, lots of questions, but maybe we don't have anything better to do in the afternoon, I suppose. So at least I don't. So I'm happy to let the discussion go on, and anyone who wants to leave is of course free to do so.
Yeah,
so as long as Andrei can has the energy to answer the questions, we can go on. Yeah. So one more from Keith, I suppose.
Hi, Andrei. Good to see you.
Yeah.
Oh, I'm there I am.
Yeah.
So actually just it's not so much a question, but just a couple of comments. You actually started to say it for the last question. So in terms of where does this come from? And of course you always have trouble with saying the words, but it's no scale supergravity, right? In no scale supergravity. And you even mentioned it a little bit earlier, that the form of the Keller potential, which you said, which are equivalent, either the t plus t star minus phi squared or 1 minus, whatever squared.
Yeah.
All of those can be, well, they're equivalent, but those will lead to these exact type of forms of potentials that you're talking about, very, very simply. And I'm going to mention it tomorrow. I mean, it's not the subject of my talk tomorrow, but
yeah.
That, with a very simple superpotentials and using the no scale formulation, which also, by the way, addresses Scott's comment about the eta problem, because the eta problem in no scale supergravity is naturally absent because you have naturally vanishing scalar masses in that case. But you get these potentials, you get the, extremely simple formulation of, the Starobinsky. I know you know all this, but I'm saying this for others that, with no scale supergravity and very simple West-Zumino form of the superpotential, you'll get Starobinsky potential, you'll get all of these alpha attractors as well.
Yeah, that's completely true. And in your models together with Elias, Nanopoulos, and others, you did something similar. Whether it was exactly similar and whether what is exactly Starobinsky, I believe that it was not exactly Starobinsky model. So these are slightly different approaches with some subtleties differentiating them. And there are some approaches which I prefer for a lot of historical reasons. But it's absolutely true that there are several different ways coming to very similar conclusions.
The other comment is a little bit more of a minor technical thing. The bands that you show, the sort of the vertical bands that you show going up, typically, and you're not the only one. Typically, people show it, where the borders of the bands are between 50 and 60 for a number of e-foldings. And you have to be a little bit careful with that, because once you have and it's fine if you're doing something generic to say, it should be between 50 and 60, but once you have a specific model, then the number of e-foldings has to be related, for example, to the reheating temperature, the equation of state, and all of these things. And typically in these models, you can't get 60, right? It's really more likely between 45 and 55. Otherwise, you have, to get to 60, you need, some non-perturbativity, to get high enough reheating temperatures to get that.
Exactly.
Yeah, so here, this is more realistic, having 47 to 57, but I think it even pushes it a little bit farther to the left.
Yeah, historically, I have shown it this way. Of course, we calculated it for any n, but historically, I've shown it that way because the data which were provided by us by Planck and by BICEP, they were oriented for this comparison for 50 to 60. So I wanted to compare it with them. But here is the situation, what happens when it is from 47 to 57 years.
Right. And the other thing is that it probably doesn't go completely straight. It probably bends a little bit because there's probably some alpha dependence in NS that's not included, for a constant n star.
Here you see two different regimes. Of course, if you have tangent, then it is almost exactly directly down.
It's not. It does bend at the bottom. It bends a little bit.
Okay, I'm at the bottom. It becomes as straight as absolutely. But here, when I guess that's the reason that we studied slightly different models, maybe. Okay, but. Or maybe it's different, whatever, I don't know.
I think it's a question of approximation.
For E models, I didn't use a slow roll approximation when I calculated numerical data, okay? But for E models, it's certain that it bends pretty substantially, mostly the upper part of it.
Well, I'll show our graphs, but it's just a question of approximate. It's a small point.
Yeah.
Okay, thank you, Keith. And hi, by the way. And Alexei has one more question.
Okay, actually, also, it's not a question, it's also a continuation of comment by Kate. Actually, because indeed, speaking about such exact numbers of capital N as say 50 or 60, it's not only inflationary model, it's inflationary models with some assumptions about reheating in particular.
Absolutely, that's what I said. Yeah.
Yes, indeed. Speaking that my model gives, I would say, as I showed in my talk, and 55 is with additional assumption that the main process of preheating is the scalar on decay into minimally coupled scalar particles. But if I, in the spirit of the Higgs model, assume in the spirit of non-minimally coupled Higgs model, assume that the decay in the same R plus R squared models, the main process of decay is going for strongly coupled scalar particles, when I would obtain 55. And actually, it will just occur as a particular case in another model which I mentioned, which in fact a mixture of R squared and Higgs. And so once more, statement about N, statement with some additional assumptions about what occurs after inflation.
Absolutely.
Yeah, I completely agree with that. And I will just give you an example of that, which is not broadly known. If you consider models of these attractors or whatever, which ends with a long stage of kination, like if you have it dark energy instead of just rolling down and oscillating, then you can increase your effective value of NS by the amount which is equivalent to approximately half of this area from 10 to. So you effectively can increase the value of N by approximately 10. It is, of course, it requires very specific models with very specific mechanism of reheating, etc. But it's not a joke. By studying this quintessential inflation, you can substantially increase the amount of N.
Okay, it looks like we have finally exhausted the questions. There were so many. It's a very nice discussion. Really happy to chair this session. Thank you for all the speakers. Thank you, Alexei and Andrei.
Thank you very much, everybody.
Fantastic talks. Oh yeah, clapping. So yeah, big hand.
Thank you too.
For all the speakers.
Thank you. Goodbye.
And
Goodbye.
Yeah, have a nice day, afternoon, evening, or whatever, wherever you are.
Thank you, and thank you very much for Kim for chairing the session. Yeah, I just wanted to thank you for chairing the session. Thanks a lot.
Okay, thanks.
Bye-bye.
Bye.
Bye.
How do I go?
Пока, Андрей, счастливо тебе. Рад тебя видеть.
Счастливо тебе тоже.
Давай, удачи.
Так, как я отсюда уйду?
Иди в митинг справа.
Ага, я. Пока.